On July 1st, 2025, a telescope in Chile caught something moving. 4 images, 17.8 magnitude, a faint dot drifting against the stars. The astronomer reviewing the data flagged it immediately. Possible near-Earth object. Possible threat. Within hours, the alert went out, and observatories around the world turned their instruments toward this tiny speck of light. What they found would challenge everything we thought we knew about visitors from beyond our solar system. Before we dive into this story, I want to ask you something. Wherever you are right now, listening to this, take a second and hit that like button and subscribe if you haven't already. Tell me in the comments where you're listening from, what time it is there, and which telescope image of 3i Atlas you find most mysterious. Want to help our community grow? Share this video and hit that notification button. Your support makes these deep dives possible. Thank you. Today's episode has 2 parts. In the first 40 minutes, we'll cover 3i Atlas, and in the second part we'll dive deep into everything new in science. If you want to skip ahead, just use the timestamp. The telescope that spotted it first was part of the Asteroid Terrestrial Impact Last Alert System, ATLAS for short. 4 robotic eyes scattered across the planet, constantly scanning for rocks that might have our name on them. The Chilean station at El Source Observatory picked up the object on images that looked unremarkable at first, just another dot among millions. But the software that analyses these frames noticed something off about its trajectory. This thing was moving fast, wrong direction, wrong speed. When they backtracked through archived observations, they found it hiding in images dating back to June 14th. It had been there for weeks and nobody knew. The Zwicky Transient Facility at Palomar Observatory in California had captured it too, multiple times, without realizing what they were looking at. Same with ATLAS stations in South Africa and Hawaii. Once you know where to look, you can find ghosts in old data. Within 48 hours, astronomers had enough observations to plot its path, and that's when the excitement turned to something else. This object wasn't orbiting our sun, it was passing through. Hyperbolic trajectory. The mathematics were clear. 3i Atlas came from somewhere else, and after its brief visit it would leave forever. Only 2 objects like this had ever been confirmed before. 1i Oumuamua in 2017, that strange tumbling cigar shape that accelerated without explanation. 2i Borisov in 2019, the comet that actually looked like a comet, complete with tail and outgassing. Now we had number 3. And from the very first observations, 3i Atlas was already showing signs of being different from both its predecessors. It was brighter than it should be, bigger than expected, and moving faster than either of the previous interstellar visitors. 2 days after discovery, the European Southern Observatory's Very Large Telescope in Chile's Atacama Desert locked onto the target. The VLT is exactly what it sounds like. 4 massive mirrors, 8.2 meters each, working together in the driest place on Earth where the atmosphere barely interferes with starlight. Over 13 minutes on the night of July 3rd, they captured multiple exposures showing 3i Atlas crawling across the background stars. When these images were stacked into a composite, you could see the comet's movement as a dotted line, each dot representing a snapshot in time. The close-up from that same night revealed early structure, not just a point of light anymore, but something with dimension, a fuzzy glow surrounding a brighter core. The coma was already forming, even though the comet was still beyond the orbit of Jupiter, more than 4 astronomical units from the Sun. That fuzzy appearance told astronomers they were looking at a real comet, not just a bare rock like Oumuamua had appeared to be. Comets are dirty snowballs, ice and rock mixed together, and when sunlight warms them, the ice sublimates directly from solid to gas. That gas carries dust particles with it, creating the cloud we call a coma. The fact that 3i Atlas was already active at such a great distance meant it contained volatile materials, chemicals that evaporate easily. But what chemicals exactly? That's where things started getting interesting. The Gemini North Telescope in Hawaii brought its multi-object spectrograph to bear on the target in mid-July. Gemini North sits at nearly 14,000 feet elevation on Mauna Kea, above 40% of Earth's atmosphere. When you point a spectrograph at an object, you're not just taking a picture. You're splitting its light into a rainbow, and every chemical element leaves fingerprints in that rainbow. Dark lines where specific wavelengths get absorbed, bright lines where they get emitted. The Gemini data gave scientists their first detailed look at what 3I Atlas was made of, or at least what it was releasing as gas. The observations used red, green and blue filters to build up a colour image, and what they saw was a comet with an unusually large coma for its distance from the Sun. The spectroscopic data revealed chemical signatures that didn't quite match typical solar system comets, but at this early stage nobody was ready to call it anomalous yet, just interesting. Then Hubble got involved. On July 21st, 2025, the Hubble Space Telescope, humanity's most famous eye in the sky, turned its attention to 3I Atlas. The comet was 277 million miles from Earth at the time, approaching the inner solar system but still far outside Mars' orbit. Hubble's wide-field camera captured what remains the sharpest image ever obtained of this object. In the picture, 3I Atlas appears as a teardrop-shaped cocoon of dust and gas, glowing against the black of space. The background stars are streaked into lines because Hubble was tracking the moving comet, keeping it centered while everything else blurred past. This is where things started looking genuinely strange. The teardrop shape itself wasn't unusual. Comets often develop asymmetric comas as they warm up, but the direction of the elongation caught attention. The dust cocoon was extended toward the Sun, not away from it. Every comet has a tail that points away from the Sun because solar radiation pressure pushes dust and gas outward. It's one of the most basic facts about comets. Their tails always point away from the Sun, like windblown hair. Except 3I Atlas had something pointing the wrong direction, an anti-tail, a sunward extension that defied the basic physics everyone understood. At first, some astronomers suggested it might be an optical illusion, a projection effect caused by our viewing angle. Sometimes dust trails can appear to point toward the Sun if you're looking at them from the right angle, even though they're actually pointing away in three-dimensional space. But detailed analysis of the Hubble image showed this wasn't geometry. The extension was real, 2-to-1 elongation as projected on the sky, which translated to roughly 10-to-1 elongation in actual three-dimensional space. Something about 3I Atlas was creating a jet of material that pointed toward the Sun, and nobody had a good explanation yet. The Hubble observations also allowed astronomers to constrain the size of the nucleus, the solid icy core at the heart of all that gas and dust. By measuring the total brightness and estimating the albedo, how reflective the surface is, they calculated that the nucleus diameter couldn't be smaller than 440 meters and couldn't be larger than 5.6 kilometers. That's a huge range, but it told them something important. 3I Atlas was substantially bigger than Oumuamua, which had been maybe a few hundred meters across at most. If 3I Atlas sat at the larger end of that estimate, it could be 1,000,000 times more massive than the first interstellar visitor. 1,000,000 times. That kind of size difference wasn't just notable, it was statistically weird. You'd expect to find small objects more often than giant ones, just like you find more pebbles than boulders. Yet here we were discovering interstellar objects, and only the third one was turning out to be potentially enormous. August 6th, 2025. The James Webb Space Telescope, the most powerful infrared observatory ever built, observed 3I Atlas with its near-infrared spectrograph. Webb sees in wavelengths invisible to human eyes, heat signatures and molecular vibrations that reveal chemical composition with stunning precision. The instrument captured spectral data across the range from 0.6 to 5.3 micrometers, building up a detailed chemical inventory of the gases surrounding the nucleus. What Webb found was unprecedented. The coma around 3I Atlas was dominated by carbon dioxide. Not water, carbon dioxide. In most comets, water ice makes up the bulk of the volatile material. When they warm up, they release water vapour as their primary gas, along with smaller amounts of other compounds. But 3I Atlas was releasing 87% carbon dioxide by mass, only 9% carbon monoxide, and just 4% water. 4%. That ratio is 16 times more extreme than what you'd expect for a typical comet at the same distance from the Sun. Some comets have slightly elevated carbon dioxide levels, sure, but nothing like this. 3I Atlas was behaving as if it formed in a completely different kind of environment, maybe close to a carbon dioxide ice line in its home star's protoplanetary disk, or maybe exposed to intense radiation that altered its surface chemistry over billions of years. The Webb data also showed enhanced outgassing specifically in the direction toward the Sun, confirming that the anti-tail feature was real and active. The spectral images mapped out carbon dioxide at 4.3 micrometers wavelength, water at 2.7 micrometers, and carbon monoxide at 4.7 micrometers. Each gas glowed in its characteristic infrared signature, painting a picture of a comet that was chemically bizarre. Mass loss rates calculated from the Webb spectrum indicated that 3I Atlas was shedding 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, and 14 kilograms of carbon monoxide per second. Total mass loss about 150 kilograms every second, which sounds like a lot until you realise the nucleus potentially weighs 33 billion tons. At that rate, the comet could keep outgassing for years without losing a significant fraction of its mass. Over the months from July through October, it would lose approximately 2 million tons total, which amounts to less than 0.00005 of its total mass. Just a surface layer averaging 4 centimeters thick across a 5-kilometer diameter object. The comet was barely scratched. While Webb looked in infrared, NASA's SphereX spacecraft captured 3I Atlas in near-infrared wavelengths between August 7th and 15th. SPHEREX, the spectrophotometer for the history of the universe, Epoch of Reionization and Ices Explorer, is designed to map the entire sky looking for water ice and organic molecules. When it turned toward 3I Atlas, it detected an extended carbon dioxide plume stretching out to at least 348,000 kilometers from the nucleus. That's almost the distance from Earth to the Moon. The carbon dioxide cloud was enormous, far larger than anything visible in optical wavelengths. SphereX also helped constrain the nucleus size by measuring scattered sunlight at 1 micrometer wavelength. If the dust plume made only a small contribution to the total brightness, the nucleus diameter could be as large as 46 kilometers for an albedo of 5%. If true, that would make 3I Atlas truly massive, a small world rather than a mere comet. On August 24th, the Keck 2 telescope in Hawaii brought its cosmic web imager to the target. Keck observations spanned the wavelength range from 0.3425 to 0.55 micrometers, capturing visible and near ultraviolet light. The resulting images showed the coma and confirmed the continued presence of the anti-tail feature pointing toward the Sun. But the real surprise came from the spectroscopic data. Keck detected prominent emission from nickel atoms in the gas around 3I Atlas. Nickel. Not particularly weird by itself, since nickel is a common element and small amounts show up in some comet spectra. Except Keck also looked for ion emission and found nothing. No ion lines at all. Every other comet ever studied, including the previous interstellar comet 2I Borisov, shows iron and nickel together if they show up at all. The two metals are chemically similar, and almost always occur together in cosmic materials. But 3I Atlas had nickel without iron, a ratio orders of magnitude different from anything seen before. The spectral features matched nickel emission, and separately the data revealed cyanide molecules in the coma. The nickel emission extended out to an exponential radius of about 600 kilometers, while cyanide spread to roughly 840 kilometers. The nickel was more centrally concentrated, suggesting it was coming directly from the nucleus, rather than being produced by chemical reactions in the outer coma. Mass loss rates for these trace species were tiny compared to the carbon dioxide. 0.9 grams per second for nickel, 3.9 grams per second for cyanide. But their presence and unusual ratios added to the growing sense that 3I Atlas was not a normal comet, not even a normal interstellar comet. Here's why the nickel without iron thing matters. On Earth, nickel without iron occurs in industrial processes where nickel is refined from ore, using a technique involving nickel tetracarbonyl, a compound where nickel atoms bind to 4 carbon monoxide molecules. That process happens at specific temperatures and pressures, and is used to create pure nickel alloys for manufacturing. Nobody expected to see something resembling industrial chemistry happening in a comet from another star system. Yet the spectral data suggested exactly that. Some process in or on 3I Atlas was creating conditions where nickel could be released without iron tagging along. Whether that meant exotic surface chemistry, unusual nucleus composition, or something else entirely, nobody knew. It was just deeply weird. August 27th brought another Gemini observation, this time from Gemini South at Cerro Pachon in Chile. This session was special because it happened as part of the Shadow the Scientist program, a public outreach initiative where citizen scientists could watch live as professional astronomers conducted observations on a world-class telescope. Karen Meach from the University of Hawaii led the scientific program, with Bin Yang guiding interpretation of the spectral data and Bryce Bolin providing expertise. The public got to see real science in action, watching as the team obtained deep multicolour images through red, green, blue and ultraviolet filters. The Gemini South images revealed that 3i Atlas now displayed a distinct tail, a proper dust tail stretching away from the sun like comets are supposed to have. The tail spanned about 1/12 of the field of view, maybe several tens of thousands of kilometres long at this point. The observations provided critical data on the dust particle sizes and composition based on how light scattered off them at different wavelengths. The dust and ice of 3i Atlas appeared broadly similar to solar system comets, suggesting that whatever exotic chemistry was happening in the gas phase, the solid particles were relatively normal. It was a reminder that this object, despite its strangeness, was still fundamentally a comet, a mixture of ice, rock and dust following the basic rules of cometary physics. But then, buried in the archives, scientists found something else. The 2-metre twin telescope at Tidy Observatory in Spain's Canary Islands had captured 3i Atlas on August 2nd, combining 159 exposures of 50 seconds each into a deep composite image. This image wasn't released publicly until mid-October, but when it finally appeared on the astronomer's telegram, it showed something remarkable. In the composite, the nucleus appeared as a large black dot surrounded by a white glow representing the coma. And breaking through that glow, like a wound in the fabric of the cloud, was a sudden fan-shaped feature extending toward the sun. A jet. A massive jet of gas and dust marked in purple in processed versions of the image, blasting off the nucleus directly toward the sun. Jets are common on comets. As the surface heats unevenly, pockets of gas beneath the crust burst through weak spots, creating collimated streams of material. But jets usually spray in various directions based on the nucleus rotation and surface topography. This jet was oriented directly sunward, contributing to the anti-tail feature that Hubble and other telescopes had been tracking. Estimates suggested the jet extended roughly 6,200 miles, 10,000 kilometres, from the nucleus surface. The discovery of this jet helped explain the anti-tail, but deepened the mystery of what was causing it. Something about 3i Atlas's rotation, or its surface properties, or its internal structure, was channeling outgassing preferentially toward the sun. Models would later propose that carbon dioxide sublimation was ejecting water ice fragments that scattered sunlight efficiently, creating the visible jet. But in August, it was just another piece of a very strange puzzle. September brought observations from the Nordic Optical Telescope, another 2.5-metre instrument in the Canary Islands. These images, captured throughout September, documented a transformation that nobody had quite expected. The anti-tail that had been pointing toward the sun started to weaken. Meanwhile, a regular tail pointing away from the sun began to grow. By late September, the anti-tail had essentially disappeared, replaced by a conventional dust tail streaming behind the comet as it raced toward perihelion. David Jewett and Jane Liu, the astronomers analysing the Nordic data, noted that the mass loss rate scaled roughly with the solar radiation flux hitting the surface, consistent with carbon dioxide being the main driver of activity. As the comet got closer to the sun would jet apparently shut off or redirected, while enhanced outgassing on the sun-facing side created enough pressure to push a proper tail outward. The transformation from anti-tail to tail happened over the course of weeks, captured in image sequences that showed the evolution in near real time. This is where the story takes a turn into territory that's harder to observe from Earth. On October 3rd, 2025, 3i Atlas made its closest approach to Mars, 30 million kilometres, close enough that spacecraft orbiting Mars had a genuine shot at imaging this interstellar visitor. The European Space Agency had 2 orbiters in position, ExoMars Trace Gas Orbiter and Mars Express, and NASA had its own fleet including Mars Reconnaissance Orbiter with its powerful high-rise camera. Between October 1st and 7th, these spacecraft turned away from their usual observations of the Martian surface to hunt for 3I Atlas. ExoMars Trace Gas Orbiter succeeded spectacularly. Using its colour and stereo surface imaging system, CASSIS, the orbiter captured a series of images with 5-second exposures on October 3rd. In those images, 3I Atlas appears as a slightly fuzzy white dot moving downward near the centre of the frame as the spacecraft tracked the star field. Background stars are streaked because CASSIS was staring at a fixed point in space, letting the comet drift through the view. The dot represents the nucleus and its surrounding coma, the inner part of the gas and dust cloud that's bright enough to register on a camera designed for photographing Mars. CASSIS could not distinguish the nucleus from the coma because 3I Atlas was still 30 million kilometres away. At that distance, resolving a kilometre-sized nucleus would be like trying to see a mobile phone on the surface of Earth's moon from Earth. Impossible. But the coma, measuring a few thousand kilometres across, was clearly visible. Nick Thomas, principal investigator for CASSIS, called it a very challenging observation. The comet was 10,000 to 100,000 times fainter than the spacecraft's usual target. CASSIS is optimised for imaging the brightly lit Martian surface just hundreds to thousands of kilometres below. Pointing it at a dim, fuzzy object 30 million kilometres away pushed the instrument to its limits. But it worked. The images showed that the bright glow around 3I Atlas extended to roughly 680 kilometres from the nucleus, at least the part bright enough for CASSIS to detect. The surface brightness falls off rapidly with distance, fading into noise, so the full extent of the coma was certainly larger than what the camera could see. Still, this was a sideway view, perpendicular to the line from the comet to the Sun. From this angle, observers could see the structure of the coma in profile rather than face-on, offering a different perspective than Earth-based telescopes had provided. Mars Express, meanwhile, struggled to capture 3I Atlas. The high-resolution stereo camera aboard Mars Express had a maximum exposure time of just 0.5 seconds, compared to CASSIS's 5 seconds. That tenfold difference in light-gathering capability proved critical. 3I Atlas has not yet revealed itself in Mars Express images. Scientists are attempting to stack multiple exposures together to boost the signal, essentially adding up many faint images to bring out details too dim to see in any single frame. Whether they'll succeed remains to be seen. The spacecraft also attempted spectroscopy, using its Omega and SPICAM instruments, trying to measure the composition of the gas cloud, but it's uncertain whether the comet was bright enough for full spectral characterization. The most anticipated images, however, were supposed to come from NASA's Mars Reconnaissance Orbiter. The HIRIS camera aboard MRO is the highest resolution camera we've ever sent to another planet, capable of imaging features as small as 30 centimetres across on the Martian surface. Pointed at 3I Atlas from a distance of 30 million kilometres, HiRISE would have a spatial resolution of about 30 kilometres per pixel. That's roughly 3 times better than the best images from Keck or Hubble. At that resolution, the brightest pixel in the image would provide an excellent constraint on the actual surface area of the nucleus, finally nailing down whether we're looking at a half-kilometre rock or a 5-kilometre giant. HiRISE almost certainly observed 3I Atlas on October 2nd or 3rd, right around closest approach. The problem is those images haven't been publicly released. The US government shut down in early October, furloughing thousands of NASA workers and halting public communications. As of late October, the HiRISE data remains locked away somewhere in NASA's archives, waiting for the shutdown to end and staff to return. Scientists are eager for it. The public is eager for it. But bureaucracy has its own timeline, and 3I Atlas doesn't wait for anyone. While the professional observatories were gathering data, amateur astronomers around the world were also tracking the comet. The Interstellar Smart Telescope Network, a community of citizen scientists using AI-powered telescopes, captured images of 3I Atlas throughout July and August. Observers like Bruno Guillet, Scott Cardell, and Frank Marchese contributed data that helped track the comet's brightness and position. Unistellar telescopes automatically point themselves, stack multiple exposures in real time, and display enhanced images that make faint objects visible to amateur equipment. The comet's brightness ranged between magnitude +17 and +19 during this period. far too faint for visual observation, but accessible to modern amateur cameras. Not all amateur observations went smoothly. On October 3rd, coinciding precisely with the Mars flyby, a heavily processed image went viral on social media. The image, captured using Dobsonian telescope equipment with solar filters, showed what appeared to be unusual structure in 3I Atlas. The timing was suspicious, the maximum public interest moment, and the image quality raised red flags among professionals. Solar telescopes use specialized filters designed for observing the blindingly bright sun, not faint deep space objects. Dobsonian mounts, while excellent for visual astronomy, lack the precise tracking needed for long exposure imaging of fast-moving comets. The viral image was almost certainly a composite of many frames stacked together, and the apparent structure was likely artifacts from atmospheric turbulence, optical aberrations, and aggressive digital enhancement. When you amplify faint signals, you also amplify noise, and noise can look like structure if you want it to badly enough. The professional community quickly debunked the image, but not before conspiracy theories spread across the internet. It's a reminder that in the age of digital image processing, anyone can create something that looks impressive, but that doesn't mean it's showing you reality. A more credible amateur contribution came from astrophotographer Simeon Schmaus, who carefully stacked 20 images from the Mascamzi camera aboard NASA's Perseverance rover on Mars. In that stack, Schmaus found a faint smudge of light in the constellation Corona Borealis, close to where 3I Atlas was expected to appear in the Martian sky on October 4th. If confirmed, this would be the first detection of 3I Atlas from the surface of another planet. But confirmation is tricky. The smudge is very faint, barely above the noise level, and other candidates exist for what it might be. Without NASA's official analysis, which is delayed by the government shutdown, we can't be certain. Another image from Perseverance's right navigation camera went viral, showing a streak of light in the Martian sky captured on October 4th at 21:33 Martian local time. The streak appeared cylindrical, elongated, and some social media users immediately declared it evidence that 3I Atlas is not a comet but something artificial. Avi Loeb, the Harvard astrophysicist who has been vocal about the possibility of 3I Atlas being technological, analysed the image and explained that the cylindrical appearance is an artifact. The navcam has an angular resolution of 0.33 milliradians, about 68 arc-seconds per pixel. At 3I Atlas's distance of 38 million kilometres, that translates to roughly 12,500 kilometres per pixel. The streak in the image spans about 4 pixels, making it roughly 50,000 kilometres long. But the actual nucleus of 3I Atlas is at most a few kilometres across. The streak isn't the comet itself. It's the result of stacking hundreds of navcam images over about 10 minutes while the comet moved across the sky. Each individual snapshot would show 3I Atlas as a circular spot, but when you combine many images taken over time while tracking the background stars, anything moving gets smeared into a line. It's exactly the same effect that creates star trails in long exposure photography if you don't track the stars. The comet moved, the camera didn't follow it precisely, and the result was a cylindrical-looking artifact. Not a spacecraft, just image processing revealing the motion of a natural object. Even as amateur and professional observations accumulated, one more eye was watching from space. NOAA's GOES, 19th satellite positioned in geostationary orbit monitoring Earth's weather, carries a coronagraph called CCOR-1. Coronagraphs are designed to block out the sun's overwhelming glare so that the faint corona and nearby objects become visible. In late October, as 3I Atlas passed behind the sun from Earth's perspective, citizen scientist Warachati Boonplod discovered the comet in CCOR-1 images. For a brief window, this coronagraph was the only instrument on Earth or in near-Earth space capable of observing 3I Atlas. The comet appeared as a faint dot moving through the field of view, heading toward perihelion on October 29th. Once it passed perihelion and emerged on the other side of the Sun in November, ground-based telescopes would be able to pick it up again. But during this critical period, GOES 19 provided the only eyes on target. Every telescope that observed 3I Atlas revealed something new, something unexpected, the anti-tail that transformed into a regular tail. The carbon dioxide dominance where water should be, the nickel without iron. The sheer size, potentially 1,000,000 times more massive than Oumuamua. Each wavelength, each instrument, each perspective added another piece to a puzzle that wasn't coming together into a coherent picture. Instead, the picture seemed to fragment further with every observation. 3i Atlas wasn't just unusual for an interstellar object, it was unusual compared to anything, period. And now, as of late October 2025, the comet has passed behind the Sun. It reached solar conjunction on October 21st, positioned exactly opposite Earth on the far side of our star. 8 days later, on October 29th, it arrived at perihelion, 130 million miles from the Sun, just inside the orbit of Mars. At that distance, sunlight delivers more than 33 gigawatts of power to the comet's surface. 33 gigawatts. For comparison, that's roughly a third of the total power output of all 94 commercial nuclear reactors operating in the United States. All that energy slamming into a 5-kilometre ball of ice and rock, heating it, cracking it, boiling away its surface. If 3i Atlas is a natural comet, perihelion should trigger dramatic outgassing, maybe even fragmentation, if the thermal stress is too much for its structure to handle. If it's something else, well, perihelion is also the optimal time for an Oberth manoeuvre, a propulsive burn at maximum velocity to change trajectory most efficiently. Coincidence or design? We can't see it right now. The Sun is in the way. November will bring new observations as 3i Atlas reappears in the morning sky. The JUICE spacecraft will fly within 64 million kilometres on November 4th, offering the first post-perihelion data. Ground-based telescopes will pick up the comet around November 11th once it emerges from the Sun's glare. By December 19th, 3i Atlas will make its closest approach to Earth, 168 million miles, still too far to pose any threat, but close enough for detailed study. And in March 2026, as the comet speeds outward past Jupiter, the Juno spacecraft will observe it from 54 million kilometres away, providing one last dataset before 3i Atlas leaves the solar system forever. But for now, in late October 2025, we're in the dark. Literally. The comet is behind the Sun, doing whatever it's going to do, and we can only wait and wonder. Every image captured so far has told us that 3i Atlas is not behaving like we expected. The question is whether the next round of images, when we finally get them, will resolve the mysteries or deepen them further. Based on the pattern so far, I'm betting on deeper mysteries. This is a comet that refuses to make sense, and the more we look at it, the stranger it becomes. Think about that for a moment. We've turned the most powerful instruments humanity has ever built toward this object. Hubble Webb Keck, Gemini, Very Large Telescope, spacecraft orbiting Mars. And instead of understanding it better, we're more confused than when we started. That's not how science usually works. Usually more data means clearer answers, but 3i Atlas seems to operate by different rules. Every answer raises 2 new questions, every solution reveals a deeper problem. The images we have are extraordinary. Teardrop comas and sunward jets and carbon dioxide plumes stretching halfway to the moon. Nickel emissions that look like industrial chemistry. A tail that points the wrong direction and then switches to point the right direction. Fuzzy dots captured from Mars orbit. Streaks across the Martian sky. Coronagraph glimpses as the comet vanishes behind our Sun. Each image is a snapshot of something that shouldn't exist, something that came from beyond our borders and brought with it chemistry and physics that don't match our expectations. And here's what keeps me up at night. We almost missed it. If Atlas hadn't been running its automated survey that night in July, if the software hadn't flagged the trajectory as unusual, 3i Atlas might have passed through the inner solar system completely unnoticed. We would never have known it was here. All those anomalies, all that strange chemistry, all those questions about where it came from and what it's made of, gone forever without us ever realizing we'd been visited. How many other interstellar objects have come and gone in the centuries before we had the technology to spot them? How many more will pass through regions of the solar system we're not watching carefully enough? 3i Atlas is only the 3rd confirmed interstellar visitor, but estimates suggest objects like this pass through the inner solar system every few years. We're only just now reaching the point where we can detect them reliably. And what we're detecting is bizarre. The visual record of 3i Atlas is a testament to human ingenuity and cooperation. Telescopes on multiple continents, spacecraft orbiting 2 different planets, amateur observers and professional researchers all contributing data. Within weeks of discovery, we had observations spanning radio to ultraviolet wavelengths, composition measurements, size constraints, trajectory tracking. That's unprecedented. When Oumuamua passed through in 2017, we barely caught it on the way out. Most observations came after it was already leaving, too far and too faint to study in detail. 3i Atlas, we caught it on the way in, months before perihelion, giving us time to mobilise every available resource. And what we've documented is a comet that challenges our understanding of what comets can be. So as we wait for the November observations, as we anticipate the JUICE flyby and the ground-based follow-up, and eventually the Juno encounter next spring, remember what every image has taught us. 3i Atlas is not playing by our rules, it's showing us chemistry we've only seen in factories. It's demonstrating behaviours we thought were impossible. It's bigger and faster and weirder than it has any right to be. And whatever it does next, whatever the post-perihelion observations reveal, I guarantee it won't be what we expect. Because this comet has made a habit of defying expectations since the moment we discovered it. The images tell a story, but it's a story written in a language we're still learning to read. Every telescope adds a new word, a new phrase, a new fragment of grammar. But the full translation remains elusive. We can see what 3i Atlas is doing. We just don't understand why. Not yet. Maybe the next round of observations will crack the code. Or maybe they'll just add more vocabulary to a language that refuses to resolve into meaning. Either way, the images we have are already historic. The first detailed visual record of a massive interstellar comet passing through our celestial neighbourhood, captured by the greatest assemblage of astronomical technology humans have ever deployed. And if nothing else, they're beautiful. Cosmic beauty with an edge of menace. Because we still don't know what we're looking at. We only know it came from somewhere else, and it's not like anything we've seen before. Picture this. A metallic sphere crashes through power lines in a quiet Colombian town, its surface etched with symbols no living human has ever seen. For 7 months, scientists, linguists, and researchers worldwide have been locked in a battle to decode what might be the most important message ever sent to humanity. And just days ago, something changed. The patterns started making sense. The translations started converging. What they're finding is not what anyone expected. Some are calling it a warning, others an invitation. But everyone agrees on one thing: we're running out of time to understand it. Before we dive deeper into what these latest breakthroughs reveal, I need your help to keep bringing you these stories. If you find value in what we uncover here, please hit that like button and subscribe to the channel. Now tell me in the comments where you're tuning in from, what time it is in your corner of the world, and here's today's question. If you could ask one question to whoever sent the Boogosphere, what would it be? And if you want to support this community's growth, share these videos and hit that hype button below. Thank you for being here. The Boogosphere, decoding the impossible. The sphere sits in a vault in Mexico City right now, 20 inches across, weighing somewhere between 4 and 10 pounds depending on when you measure it. That weight fluctuation alone defies every principle of classical physics we've built our understanding upon, but we'll return to that particular impossibility in a moment. What matters most today, what has the scientific community and conspiracy researchers alike buzzing with equal intensity, is what happened in the last 48 hours with the translation efforts. You already know the basics. March 2nd, 2025, Buga, Colombia. Farmer Jose Rompo witnesses something zigzagging through the sky. Not the smooth arc of a ballistic object, not the steady cruise of an aircraft. A pattern that suggests intelligence, decision-making, active navigation, then contact with high-tension wires, sparks, a crash. And Jose, showing either remarkable courage or remarkable foolishness, picks up the sphere while it's still cold enough to feel like opening a refrigerator door. The symbols around its equator have haunted researchers ever since. 20+ distinct characters arranged in a band, each one unique, machined with a precision that suggests technology far beyond simple engraving. Under magnification, the edges are perfect. No tool marks, no variance in depth, as if the metal itself was convinced to form these shapes rather than cut or etched into them. For months, the conversation circled the same questions. Are these letters? Pictograms? Mathematical notation? Some argued they resembled ancient scripts, Proto-Sanskrit, Ogham, even Mesopotamian cuneiform. Others insisted the geometric precision pointed towards something more functional, circuit patterns, navigational coordinates, quantum information encoded in angles and spacing. Then came the artificial intelligence analyses. Multiple teams, working independently, fed high-resolution images of the symbols into language models trained on every known writing system in human history. And here's where it gets fascinating. The AI systems initially rejected the symbols as language. Too much decoration, zero repetition of characters, no clear word boundaries or grammatical structure. Everything that makes a writing system functional for communication was absent. But one researcher, whose work appeared on specialized forums just last week, took a different approach. Instead of treating each symbol as a letter, what if each symbol was a word? Or more precisely, what if the entire circular arrangement was a single compressed message, with meaning encoded not just in the shapes, but in their angular relationships to each other? The breakthrough came from analysing the geometry. The symbols aren't evenly spaced. Some clusters sit closer together, others spread apart. When you map the angular distances between symbols, patterns emerge. Ratios, Fibonacci sequences appearing in the spacing, golden angles, the kind of mathematical relationships that appear in nature, in the spiral of a nautilus shell, in the arrangement of seeds in a sunflower head, in the structure of galaxies. One translation that's gained serious traction, and I want to be clear this is still debated, heavily debated, suggests the phrase artificing Earth, ship 12. Now pause on that for a moment. Artificing. Not visiting, not observing, artificing. The act of making artificial, of transforming something natural into something constructed, designed, intentional. If this translation holds, and that's still a significant if, it suggests the sphere isn't a message about Earth. It's a message about what's being done to Earth, the modification of a planet, and Ship 12 implies this isn't a solo mission. There are at least 11 others, maybe more. But other researchers arrived at completely different conclusions. Another AI-assisted translation team reported the phrase, "Beware the sky," signal received. Shorter, more ominous, a confirmation that something was heard, acknowledged, and now, perhaps, something is coming. The warning interpretation aligns with the more mystical translations that began circulating in July, messages about transformation, unity, consciousness. Spiritual language that sounds profound but lacks the specificity you'd expect from an advanced civilization trying to communicate across cosmic distances. Dr. Jose Luis Velasquez led the team that produced what they call the godlike message. The origin of birth through union and energy in the cycle of transformation, the meeting point of unity, expansion and awareness, individual consciousness. Beautiful words, poetic even. But here's the challenge. If you wanted to warn humanity about an impending threat, would you speak in spiritual abstractions, or would you be specific? Clear, urgent. This is the paradox researchers keep hitting. The sphere's physical properties scream advanced technology. The internal structure revealed by X-rays shows 3 distinct density layers forming an elongated shape. Some compare it to a Tesla coil laid on its side. Others see biological structures, something almost organic in how the components nest within each other. Fibre optic-like strands woven through the shell, terminating at points across the surface that could be sensors or emitters. These aren't the characteristics of art. This is engineering, functional technology. Yet the message, if it is a message, speaks in metaphor and poetry. Why? One possibility that's been quietly gaining support in certain circles, though you won't see it in peer-reviewed journals yet, is that the sphere isn't communicating with humans at all. At least, not primarily. What if it's a beacon? A signal device meant to be triggered by specific conditions, broadcasting to something or someone else entirely? The electromagnetic emissions detected early on support this. Oscillating frequencies, patterns that repeat but vary slightly each cycle. The language of a transmission, not a translation. If the sphere is broadcasting, what is it saying? And who's listening? The weight anomaly becomes crucial here. Initial measurements put the sphere at roughly 4.5 pounds, 2 kilograms, small enough to carry easily. But as it sat in examination, as it was handled and studied, witnesses reported the weight increased. By the time it reached Mexico City, calibrated scales registered 10 pounds, more than double, with no change in size, no material added, just mass appearing, accumulating, as if the sphere was drinking something invisible from the air around it. One engineer at the June press conference, Rodolfo Garrido Cottom, proposed it might be an anti-gravity drive shutting down. As the propulsion system lost power, conventional mass reasserted itself. The sphere wasn't gaining weight, it was losing the field that made it light. Think about that. An object that can modulate its own relationship with gravity. The implications for physics are staggering. The implications for travel, for energy, for our understanding of mass itself are revolutionary. But if it's tech this advanced, crashing into power lines seems, well, clumsy, doesn't it? Unless the crash wasn't an accident. Unless the sphere was meant to be found, meant to be studied, meant to generate exactly the kind of attention and debate it's creating right now. Stephen Greer, founder of the Disclosure Project, has been one of the sphere's most vocal advocates. He's linked it to what he calls electrogravitic fields, suggesting the technology operates on principles that human physics is only beginning to understand. Greer also made waves by claiming that fake policemen, whoever that means, attempted to break into the vault where the sphere is stored. No independent confirmation of that claim exists, but it adds another layer to the story. If true, it means someone wants the sphere badly enough to risk exposure. If false, it's an excellent way to generate publicity and mystique. The authentication battle raging around the sphere mirrors every major UFO case in history. Believers point to the seamless construction, the material composition showing rare Earth elements that weren't discovered until the 19th century yet are somehow present in what some claim is a 12,000-year-old artifact. Skeptics counter that modern 3D printing and advanced metallurgy could produce every feature the sphere displays. They point to the convenient timing, appearing during a surge in UFO interest. They note the involvement of Jamie Maussan, the Mexican journalist who previously promoted mummified aliens that turned out to be modified animal remains. Here's what we can verify. The sphere exists. Its physical properties are unusual enough that multiple scientists have gone on record expressing confusion. The symbols are real, machined with precision that exceeds most commercial capabilities. The electromagnetic emissions were detected by multiple instruments, and the weight change, whether you believe it's anti-gravity shutdown or some other mechanism, was witnessed by numerous observers using calibrated equipment. What we can't verify yet is origin, purpose, message. Those remain in the realm of interpretation, and interpretation is where science ends and belief begins. But new data keeps arriving. Just last week, another research team announced they'd detected what they're calling response signatures from the sphere. When exposed to specific sound frequencies, particularly certain Sanskrit chants, instruments registered changes in the sphere's electromagnetic output, as if it was listening, processing, responding. The team describes it as the sphere singing back. Now, this is where we need to tread carefully. Sound causing physical responses in materials isn't magical. Resonance is real. Every object has frequencies at which it naturally vibrates. Match that frequency and you get amplification, response, sometimes destruction. Opera singers shattering wine glasses, bridges collapsing from wind vibrations. These are known phenomena, so the sphere responding to sound could be coincidence, the researchers accidentally hitting resonant frequencies. Or it could be design, built to react to specific acoustic signatures as a kind of lock and key system. If it's the latter, what else might activate it? What other keys exist? And what happens when you turn them? The June 2025 press conference in Mexico City brought together an unusual coalition. Mexican scientists, US Representative Eric Burleson, Stephen Greer, Attorney Daniel Sheehan, all standing behind the claim that this represents something beyond conventional explanation. Representative Burleson made an interesting point. He contrasted the transparency around the Boogosphere investigation with what he described as stonewalling in the United States. We've been blocked in Congress, he said. We've been blocked from receiving the briefings that we need. That statement connects the Boogosphere to the larger disclosure movement gaining momentum throughout 2025. The idea that governments possess knowledge of non-human intelligence and have systematically concealed it. Whether you believe that narrative or not, the fact that elected officials are saying these things publicly, on record, represents a shift. The conversation has changed. And the boogosphere sits at the centre of that conversation, tangible, physical, testable, and utterly confounding. The linguistic analysis continues to evolve. One researcher, posting detailed work on specialised forums, described running a frequency analysis on the symbols, not treating them as letters, but as data points in a larger pattern. The results suggested what he called geometric encryption, meaning stored not in what the symbols are, but in how they relate spatially. Imagine a musical score where the notes matter less than the intervals between them. The harmony, the resonance, the mathematical relationships that create the music. If the sphere's message is geometric, it would explain why traditional linguistic approaches fail. You can't translate math. You can only solve it, and solutions require understanding the rules of the system. What if we're trying to read a message written in a mathematical language we don't fully grasp yet? The involvement of artificial intelligence in decoding attempts raises its own questions. These language models are trained on human communication, human patterns, human logic. They're incredibly sophisticated at finding patterns in data that matches their training. But what happens when you point them at something genuinely alien? Something that doesn't follow human cognitive architecture? They might find patterns that aren't there. Pareidolia at the algorithmic level, seeing faces in clouds, hearing words in white noise. Or they might miss patterns entirely because they are optimized for the wrong kind of information. It's like using a metal detector to find plastic. The tool works perfectly, it's just not designed for what you're looking for. This is why the multiple contradictory translations are both frustrating and revealing. Artificing Earthship 12, beware the sky signal received, the origin of birth through union and energy. These aren't variations on a theme, they're fundamentally different messages, which suggests either the AI is struggling to find coherent meaning in noise, or the sphere's message is multi-layered, containing different information depending on how you approach it. That second possibility is worth exploring. What if the sphere is designed to communicate different things to different levels of understanding? Basic information accessible to anyone who looks. Deeper meaning requiring specific knowledge or tools, and perhaps something else entirely, hidden, waiting for the right key to unlock it. We see this in human communication too. A children's story can contain themes and meanings that only adults recognize. A scientific paper can be read at multiple levels, from general summary to technical detail. Maybe the sphere operates on similar principles. The mystical translations might be what we get at our current level. The technical translations, Artificing Earth, Ship 12, might require more context, more knowledge, more development before they make complete sense. Or maybe we're overthinking it. Maybe the sphere is exactly what the skeptics say, a well-crafted art project or hoax designed to exploit our hunger for mystery and meaning. The timing is certainly convenient. UAP hearings in Congress, documentary films about disclosure, public attention on the possibility of non-human intelligence at an all-time high. Drop a mysterious sphere into that environment and watch what happens. But that explanation requires its own leaps. It requires believing that someone created this object, with its seamless construction and unusual materials and electromagnetic properties, then orchestrated its discovery in a way that appears organic and random. It requires believing that the farmers, the local investigators, the subsequent handlers all either collaborated in the deception or were fooled by it. Possible? Yes. Simple? Not remotely. The truth, as it often does, probably sits somewhere in the complicated middle ground. The sphere is real. Its properties are unusual, but perhaps not impossible with advanced human technology. The symbols are intentional, but their meaning remains genuinely unclear. And the interpretation has become a Rorschach test, with everyone seeing what they're predisposed to see based on their existing beliefs about extraterrestrial contact, government secrecy, and the limits of human knowledge. What's undeniable is the impact. The boogosphere has captured global attention in a way few alleged anomalous artifacts have. It's testable, measurable, sitting in a vault where qualified researchers can examine it. That accessibility, that openness to investigation, sets it apart from most UFO claims that rely on distant sightings, or grainy footage or second-hand testimony. Whether it's alien technology, ancient human achievement, or elaborate modern construction, the sphere represents a challenge. a puzzle demanding solution, and humans, we're built to solve puzzles. We can't help ourselves. Show us a mystery, and we'll pick at it, prod it, argue about it until we've either solved it or exhausted ourselves trying. The latest developments suggest we're nowhere near exhaustion yet. New teams are lining up to study the sphere. New technologies are being proposed to analyse it. Quantum sensors, advanced spectroscopy, materials analysis at the atomic level. Each new tool might reveal something previous examinations missed, or might simply add more data points to an already confusing picture. And while the scientists and researchers debate methodology and interpretation, the sphere sits. Silent except for those electromagnetic whispers, heavy except when it's light, cold except for those fibre optic patterns that might be carrying information or might be carrying nothing at all, waiting for understanding, for activation, for whatever comes next. Google's quantum leap, 13,000 times faster than reality. While researchers debate alien messages etched on metallic spheres, a different kind of breakthrough happened 4 days ago that might actually reshape civilization faster than any interstellar communication could. Google's quantum computing division just demonstrated something that theoretical physicists have been promising for decades but couldn't quite deliver. They made a quantum computer perform a real, verifiable, practical calculation that the world's fastest supercomputer would need years to complete. The quantum machine did it in hours. Let me say that differently. Frontier, currently the most powerful classical supercomputer on Earth, capable of performing over 1 quintillion calculations per second, would require multiple years of continuous operation to solve what Google's Willow chip handled in an afternoon, 13,000 times faster. That's not an incremental improvement, that's a fundamental shift in what's computationally possible. The algorithm they used is called quantum echoes. The name itself hints at something profound about how it works. Imagine sending a carefully crafted signal into a quantum system, then disrupting one tiny piece of it, then precisely reversing everything and listening for the echo that bounces back. That echo gets amplified through quantum interference, where probability waves add together and strengthen instead of cancelling out. The result is information about the system's internal structure that would be impossible to extract any other way. Hartmut Neven, Google's vice president of engineering leading the quantum division, described it during the press conference with barely contained excitement. This isn't just quantum advantage on paper anymore. It's verifiable, repeatable, and it's pointing toward applications we can actually use. The algorithm produces predictions about real physical systems, predictions you can test by talking to nature directly and comparing results. When the quantum computer says a molecule should behave a certain way, you can build the molecule and check. So far, the computer's winning. Here's what makes this different from previous quantum computing claims. Back in 2019, Google announced quantum supremacy with a demonstration that critics immediately questioned. The problem they solved was essentially mathematical busywork, designed to be hard for classical computers, but with no practical application. It proved quantum computers could do something classical computers couldn't, but that something didn't matter outside the lab. This time, they're measuring physical properties that scientists actually care about. Molecular structures, material behaviours, the kind of information that drug designers and materials engineers desperately need. The breakthrough builds on their Willow chip, which they announced late last year. Willow solved a problem that had plagued quantum computing for 3 decades. As you add more qubits, those quantum bits that store information in superposition states, the error rate traditionally skyrockets. More qubits should mean more power, but it also means more opportunities for the delicate quantum states to collapse, to decohere, to lose the very quantumness that makes them useful. Researchers called it the error correction barrier, and it seemed fundamentally insurmountable. Willow broke through by implementing error correction so efficiently that adding more qubits actually reduces errors instead of increasing them. It's like discovering that adding more instruments to an orchestra makes it quieter instead of louder. Completely backwards from intuition, but exactly what the math predicted should be possible. The chip maintains quantum coherence across its entire 65-qubit array, with error rates below 0.03% for the quantum gates, the operations that manipulate the qubits. That precision is what makes the quantum echoes algorithm possible. The algorithm measures something called out-of-time order correlators. The acronym is OTOC, and if that sounds technical, well it is. But the concept is actually elegant. In classical physics, time flows in one direction. You can predict what happens next based on what's happening now. Quantum systems are weirder. Information can flow backwards through time in certain senses, not literally but mathematically. Measuring these temporal correlations reveals how quantum systems evolve, how particles interact, how energy moves through materials. Google's implementation measures the second-order version, OTOC with an exponent of 2, which captures interference effects that first-order measurements miss. These interference patterns contain information about the internal dynamics of quantum systems, information that's theoretically accessible but practically impossible to extract with classical methods, until now. The comparison to Frontier is deliberate and devastating. Frontier isn't some outdated machine, it's brand new, cutting edge, the pinnacle of classical supercomputing architecture. Exascale computing, meaning it breaks the exaflop barrier, 1 quintillion floating point operations per second. The machine costs hundreds of millions of dollars, fills a massive facility, consumes enough electricity to power a small city. And Google's quantum chip, which you could hold in your hand if it wasn't kept at temperatures colder than deep space, runs circles around it for this specific type of calculation. Now, specificity matters here. Quantum computers aren't faster at everything. They won't replace your laptop. They're not going to render video or run spreadsheets better than conventional processors. They're specialized tools for specialized problems. But those problems include simulating quantum mechanics, which means understanding chemistry, materials science, drug interactions, anything that depends on how atoms and molecules actually behave. That's not a narrow domain. That's potentially everything. The pharmaceutical industry is watching this development with intense interest. Designing new drugs currently relies on a combination of educated guessing, trial and error, and massive computational screening of possible molecules. Most candidates fail. The process takes years and costs billions. If quantum computers can accurately predict how drug molecules will interact with target proteins, how they'll fold, how they'll behave in biological systems, the entire development pipeline compresses. Drugs that would take a decade to develop might take 2 years. Treatments for rare diseases that aren't economically viable to research with current methods become possible. Materials science faces similar transformations. We need better batteries, more efficient solar cells, superconductors that work at reasonable temperatures, materials that can withstand extreme conditions. Classical simulation can only approximate quantum behavior. It's like trying to predict ocean waves using a model that doesn't include water. You'll get something, but it won't be quite right. Quantum simulation, running quantum calculations on quantum hardware, eliminates the approximation. It's not modelling the waves, it's making waves. The nuclear magnetic resonance application they demonstrated is particularly clever. NMR is a technique that's been around for decades, using magnetic fields to probe the structure of molecules. It's how we do MRI scans in medicine. It's how chemists figure out molecular structures. But conventional NMR has distance limits. It can measure short-range interactions well, but struggles with longer distances within molecules. The quantum echoes technique extends that range significantly, turning NMR into a more powerful molecular ruler. This matters because molecular shape determines function. A protein that's folded one way might catalyze a reaction. The same protein folded slightly differently might do nothing, or worse, might cause disease. Understanding structure at the atomic level is fundamental to understanding biology, chemistry, materials, everything built from atoms, which is everything. Nevin outlined a roadmap during the announcement. Short term, meaning the next 5 years, they expect quantum-enhanced sensing, better measurements of faint signals that classical detectors miss, hybrid workflows where quantum processors handle specific subtasks while classical computers do the rest, algorithms that deliver insights completely inaccessible to conventional computing, long-term, full fault-tolerant quantum computers where error rates are suppressed enough to run extended calculations on real-world problems. That long-term goal is closer now than it was, not just because of the hardware improvements, though those are substantial, but because they've demonstrated the software works. The Quantum Echoes algorithm isn't vaporware, it's running, producing results that match physical reality when you test them. The verification aspect is crucial. One of the persistent criticisms of quantum computing has been the difficulty of checking results. How do you verify that the quantum computer gave you the right answer, when you can't compute the right answer classically. It's like asking someone to grade their own homework without an answer key. Google's solution is elegant. The quantum computer makes predictions about physical systems. You then perform actual physical experiments. Nature itself becomes the answer key. This closes a credibility gap that's plagued the field. Previous demonstrations relied on mathematical proofs or classical simulations of small systems, impressive to experts but unconvincing to skeptics. Running an experiment and watching nature confirm the quantum computer's prediction is different. That's empirical validation. That's science. The hardware enabling all this sits at temperatures approaching absolute zero, 15 millikelvin. That's 15,000ths of a degree above the coldest possible temperature in the universe. At these temperatures, matter behaves strangely. Electrons in certain materials flow without resistance, superconductivity. Quantum effects that usually get washed out by thermal noise become observable, controllable, usable. The Willow chip uses superconducting circuits, loops of wire that become perfect conductors when chilled. These circuits can be engineered to behave like artificial atoms, quantum objects large enough to see under a microscope but small enough to follow quantum rules. They exist in superposition states, simultaneously representing 0 and 1 until measured. They can be entangled, linked in ways that mean measuring one instantly affects the other regardless of distance. Google's been working on this approach for years, building on decades of research by physicists exploring whether quantum effects could scale beyond the atomic realm. The answer, confirmed again with each advance, is yes. Quantum mechanics isn't just for particles. Build the right systems, isolate them properly from environmental noise, and quantum behavior emerges at scales we can manipulate. The 65 qubits in Willow represent a sweet spot, enough to demonstrate quantum advantage on meaningful problems, few enough to maintain the extreme precision required for error correction. The real push now is scaling up while maintaining quality. 1,000 qubits with the same error rates would be transformative. 10,000 would be revolutionary. Getting there requires solving materials challenges, engineering challenges, control system challenges, but the path forward is visible now in a way it wasn't before. Critics remain, of course. Some question whether the problems quantum computers solve efficiently are problems anyone actually needs solved. There's an element of truth there. Quantum computing has been a solution looking for problems since the concept emerged. But as the hardware improves, as the algorithms get more sophisticated, the overlap between what quantum computers can do and what people want done keeps growing. We've crossed from purely academic exercises into territory that matters for medicine, materials, chemistry, potentially cryptography and communication. The cryptography angle generates both excitement and dread. Current internet security relies on mathematical problems that are hard for classical computers to solve. Factoring large numbers, computing discrete logarithms, problems where the time required grows exponentially with input size. Quantum computers can solve certain versions of these problems efficiently. Not today. Not with 65 qubits. But eventually. Which means encrypted data that's secure now might become readable later when larger quantum computers exist. This has sparked a race toward quantum-resistant cryptography, new encryption schemes based on mathematical problems that even quantum computers struggle with. Standards organizations are evaluating candidates. Some have already been approved. The transition will take years, maybe decades. Meanwhile, adversaries might be storing encrypted data now with the plan to decrypt it later. Harvest now, decrypt later strategies. Anything sensitive that needs to stay secret for more than a decade faces a ticking clock. But encryption breaking, while dramatic, is almost a side effect. The main event is simulation, prediction, optimization, problems where quantum computers can explore vast solution spaces efficiently. Drug discovery, materials design, financial modeling, machine learning, climate prediction, traffic optimization, supply chain management. Anywhere you have too many variables interacting in complex ways for classical computers to handle practically. The verification achievement matters philosophically too. It demonstrates that quantum mechanics, despite its weirdness, produces reliable predictions about reality. This has been true since quantum theory emerged a century ago, but seeing it play out on engineered systems of this scale reinforces confidence in our understanding. We're not just theorizing about quantum behavior anymore. We're building machines that use it as a computational resource. The quantum echo's name carries deeper meaning. Sound waves echo because they reflect off boundaries, off interfaces where properties change. Quantum echoes arise from a similar principle. Perturbing the quantum system creates disturbances that propagate through the system, reflect off its internal structure, and return carrying information about what they encountered. By measuring these echoes precisely, you map the territory they travelled through. This connects to one of physics' fundamental insights. Information and reality are deeply intertwined. What we can know about a system constrains what the system can be. Quantum mechanics makes this explicit. Measurement doesn't just reveal properties, it actualizes them, collapses possibilities into outcomes. The quantum echoes algorithm exploits this by carefully structuring measurements to extract maximum information while minimally disturbing the quantum states. It's a delicate dance between observation and preservation. Google's demonstrated the first two steps on their roadmap. Beyond classical computation, check. Quantum error correction below threshold, check. The next milestone is a fully error-corrected logical qubit, where errors are suppressed so efficiently that the qubit can maintain coherence indefinitely for practical purposes. After that comes scaling to thousands of logical qubits, then algorithms that solve problems of genuine commercial and scientific value. Each step builds on the previous. Each validation increases confidence that the next is achievable. We're watching the early stages of a technology that might define the rest of the century. Classical computing took decades to progress from room-sized machines processing punch cards to smartphones with more power than the Apollo program's computers. Quantum computing is moving faster because it's building on that classical foundation, using conventional processors to control and read out quantum ones. The companies investing in this technology are betting billions on the payoff. Google, IBM, Microsoft, Amazon, startups backed by venture capital and government grants. China has made quantum computing a strategic priority. The European Union has launched major initiatives. This isn't speculative anymore. It's a race with real stakes, economic and strategic. And 4 days ago, Google pulled ahead in a way that's hard to dismiss. 13,000 times faster isn't hype, it's measurement. Verifiable quantum advantage on an algorithm with practical applications isn't marketing, it's a threshold crossed. The question now isn't whether quantum computers will transform technology, it's how fast and who gets there first. The 2025 Physics Nobel, Quantum Goes Macroscopic. 3 weeks ago, the Nobel Committee made a choice that finally acknowledged work that's been hiding in plain sight for 40 years. John Clark, Michel Deverett, and John Martinez won the Physics Prize for proving that quantum mechanics, that strange realm where particles tunnel through barriers and exist in multiple states simultaneously, isn't confined to the atomic scale. They showed that quantum effects can manifest in objects you could hold in your hand, see with your eyes, measure with ordinary instruments. And in doing so, they laid the foundation for every quantum computer currently being developed, including the one that just demonstrated 13,000 times speed up over classical systems. The timing feels almost orchestrated, though it's purely coincidental. Google's Willow chip, with its superconducting circuits maintaining quantum coherence across dozens of qubits, directly descends from experiments Clark and his colleagues performed in the 1980s. They asked a question that seemed almost philosophical at the time. Can something big, macroscopic in the technical sense, behave quantum mechanically, or does quantum weirdness vanish as you scale up from atoms to objects? The answer turned out to be yes, with conditions. Build the right system, cool it to near absolute zero, shield it from environmental noise, and quantum behavior emerges even in circuits containing trillions upon trillions of electrons moving collectively. Not individual particles doing quantum things, bulk matter behaving as a quantum system. Their breakthrough centered on quantum tunneling, an effect that's fundamental to modern electronics, but was thought impossible at large scales. Tunneling is what happens when particles pass through barriers they shouldn't be able to cross. Imagine rolling a ball at a hill. Classically, if the ball doesn't have enough energy to reach the top, it rolls back down. Quantum mechanically, there's a probability the ball appears on the other side of the hill without ever going over it. The particle doesn't climb or dig or go around. It just, from a certain perspective, is on both sides simultaneously until measurement collapses the superposition. At atomic scales, tunneling is routine. It's how transistors work. It's why radioactive atoms decay. It's the mechanism behind scanning tunneling microscopes that can image individual atoms. But scaling it up seemed impossible. The probability of tunneling drops exponentially with mass. A single electron might tunnel through a nanometer barrier easily. 100 quadrillion electrons doing it together? The odds become absurdly small. Unless you use superconductors. Clark, Deverett and Martinez worked with Josephson junctions, devices named for Brian Josephson, who won his Nobel in 1973, for predicting their behaviour. A Josephson junction is beautifully simple. Two superconductors separated by a thin insulating barrier. Electrons can tunnel across the barrier in pairs, Cooper pairs as they're called in superconductors, creating effects that only make sense quantum mechanically. The question was whether the entire junction, with its macroscopic currents and voltages, could tunnel between states, not individual electrons sneaking across. The whole system, quantum jumping from one configuration to another. Theorists, particularly Tony Leggett, who won his own Nobel in 2003, predicted it should be possible, but prediction and demonstration are different animals. The Berkeley experiments in the mid-80s settled it. They built circuits cold enough and clean enough that quantum effects dominated despite the large number of particles involved. They observed the junctions tunneling between voltage states, observed them existing in superposition, observed behaviour that had no classical explanation. The measurements matched quantum theoretical predictions precisely. John Clark, speaking after the Nobel announcement, expressed surprise that this work was considered prize-worthy. He led the initial research but credits the contributions of dozens of physicists who refined the techniques and pushed the boundaries. His humility aside, the impact is undeniable. Those experiments proved that quantum mechanics scales, that quantum computing isn't just theoretical fancy, that we can build machines exploiting quantum effects for computation, sensing, simulation. The philosophical implications run deeper. Erwin Schrödinger proposed his famous cat thought experiment in 1935 as a critique of quantum mechanics, not an endorsement. He found it absurd that a cat could be simultaneously alive and dead, that macroscopic objects could exist in superposition. The point was to highlight what he saw as a flaw in the theory. If quantum mechanics produces ridiculous conclusions about everyday objects, maybe quantum mechanics needs revision. But the Nobel-winning experiments showed Schrödinger was wrong about where to draw the line. Quantum mechanics does apply to macroscopic systems if you isolate them properly. The cat thought experiment fails, not because quantum mechanics breaks down, but because keeping a cat isolated from environmental interference is impossible. A cat is warm, breathing, interacting with air molecules, radiating photons. All those interactions collapse the quantum state continuously. But a superconducting circuit at 15 millikelvin, vacuum-sealed, magnetically shielded, that you can keep quantum. This resolution has profound implications for understanding consciousness, free will, the nature of reality itself, though those topics generate more speculation than science. What's concrete is that macroscopic quantum systems are real, controllable, and useful. The Nobel Committee recognized this by framing the prize around technological impact as much as fundamental discovery. Alexandra Bley, a quantum physicist at University of Sherbrooke, called it a redefinition of what quantum physics means. It's not just the theory of small things, it's a theory of isolated things. Scale doesn't matter if you maintain coherence. This opens possibilities beyond computing. Quantum sensors that detect magnetic fields with unprecedented sensitivity. Quantum communication systems that are fundamentally secure. Quantum simulators that can model systems too complex for classical computers. The sensor applications deserve attention because they are already deployed in some cases. MRI machines, magnetic resonance imaging, rely on quantum effects in atomic nuclei. But more sensitive devices based on superconducting quantum interference, SQUIDs, can detect magnetic fields so weak they'd be impossible to measure otherwise. Medical applications include magnetoencephalography, mapping brain activity by detecting the tiny magnetic fields neurons generate. Geological applications include finding mineral deposits and mapping underground structures. Military applications remain classified but presumably include submarine detection and other strategic sensing. These aren't future technologies, they're present, working, commercially available in some cases. The Nobel recognized not just the science, but the engineering that followed. Quantum electrical engineering, as Stephen Gervin from Yale described it, taking quantum mechanical principles and building practical devices. The path from basic research to application took decades. The initial experiments were pure science, testing theoretical predictions with no thought of usefulness. But physicists and engineers saw potential. If you could make a quantum bit, a qubit, you could do quantum computation. The math had been worked out in the 80s and 90s. Algorithms existed on paper showing quantum computers could factor large numbers efficiently, search databases faster, simulate quantum systems naturally. All that was missing was hardware. Superconducting circuits became a leading candidate because they leveraged existing fabrication techniques from the semiconductor industry. You could pattern them with lithography, integrate them on chips, scale production. Other approaches existed: trapped ions, neutral atoms, topological systems, each with advantages and challenges. But superconducting qubits got early traction and maintained momentum. By 1999, researchers at Nippon Electric Company in Japan built the first true superconducting qubit, a circuit that oscillated between two quantum states reliably and rapidly. The field exploded from there. Google, IBM, Rigetti, IonQ, dozens of startups and established tech giants pouring resources into quantum computing development. Martinis himself led efforts at Google before moving to UC Santa Barbara, directly contributing to the systems now demonstrating quantum advantage. The Nobel came after quantum computing proved itself viable, but before it's fully mature. This timing is strategic. Physics Nobels typically recognize work decades old, giving time for impact to become clear. But quantum computing's trajectory was obvious enough that waiting longer seemed unnecessary. The prize serves partly as validation, telling the field it's on the right track, encouraging continued investment. Critics of quantum computing, and they exist, argue that practical applications remain elusive despite enormous spending. They're not entirely wrong. The problems quantum computers solve easily don't align perfectly with problems people need solved. Factoring large numbers matters for cryptography, but little else. Simulating quantum systems matters for chemistry and materials science, domains where commercial applications are still emerging. The gap between what quantum computers can do and what generates profit or solves pressing problems is real. But that gap is closing. Each hardware improvement, each algorithmic advance, each demonstration of quantum advantage on a practical problem narrows it. Google's Quantum Echo's achievement is precisely this kind of progress. Not a toy problem, a real calculation with implications for understanding molecular structure, material properties, physical systems we care about. The Nobel Committee's citation specifically mentions macroscopic quantum mechanical tunneling and energy quantization in superconducting circuits. Energy quantization means the system can only exist in specific energy states, not a continuum, like a staircase where you can stand on steps but not between them. This discrete structure is fundamental to how qubits store information. A qubit in the ground state represents 0. In the first excited state represents 1. Superposition means it's on both steps simultaneously until measured. Demonstrating this in macroscopic circuits proved the principle. Refining it into controllable qubits took another decade. Making arrays of qubits that could be entangled and manipulated took another decade beyond that. We're now at the stage where systems with dozens of qubits are performing calculations beyond classical reach. The next stage is hundreds, then thousands of qubits with error correction good enough for extended algorithms. Each Nobel Prize represents the committee's judgment about what mattered in physics. Sometimes they recognize discoveries that obviously changed everything. Relativity, quantum mechanics, transistors. Sometimes they recognize subtler contributions that enabled larger advances. This prize falls into the second category. The experiments themselves were elegant and definitive, but not immediately world-changing. What changed the world was what followed, the technology those experiments proved possible. Think about it this way. Proving quantum tunneling happens in superconducting circuits is like proving you can start a fire by rubbing sticks together. Interesting demonstration. Validates theoretical understanding. But the real impact comes when someone builds a lighter, then a match, then a gas stove, then power plants. The Nobel recognized the people who proved the principle, but they did so knowing full well that the technology built on that principle is reshaping computation, cryptography, sensing, and simulation. One interesting aspect of the announcement was the committee's emphasis on future applications. Physics Nobels traditionally focus on what was discovered, not what might come from it. But quantum computing's trajectory is clear enough that speculation feels justified. MRI machines were mentioned, faster computers were mentioned, quantum cryptography, quantum communication, quantum simulation, all received nods. This forward-looking framing might reflect changing attitudes about science's role. Pure research for its own sake has become harder to justify politically as funding pressures increase. Demonstrating practical value, even potential value, helps maintain support. The quantum computing field has benefited enormously from government and private investment, precisely because the applications seem real and valuable, even if they are not fully realized yet. The three laureates represent different pieces of the puzzle. Clark built the experimental apparatus and pushed measurement sensitivity to levels that revealed quantum behavior. Deverett worked on the theoretical frameworks and developed techniques for controlling quantum circuits. Martini's focused on reducing noise and improving coherence times, making qubits stable enough for computation. Collaboration across expertise enabled the breakthrough. No single person could have done it alone. This collaborative aspect is increasingly common in physics. The days of lone geniuses revolutionizing understanding are largely past. Modern physics requires teams, specialized equipment, diverse skill sets. The Nobel Committee tries to honor individuals despite this reality, often awkwardly. Three-person limit means many contributors get overlooked. This prize explicitly mentions that many physicists advance the field, even though only 3 can receive the award. Public reaction to the Nobel was mixed. Physics enthusiasts celebrated seeing quantum computing validated at the highest level. Skeptics questioned whether engineering achievements deserve Nobel recognition, preferring pure discovery. The broader public mostly shrugged. Quantum computing remains abstract and confusing to most people despite its potential importance. Explaining why circuits acting quantum mechanically matters requires background most don't have. But the physics community understood the significance immediately. Decades of work validated. A clear signal that this path leads somewhere important. And timing aligned with major advances, making the award feel current and relevant rather than historical recognition of dusty old experiments. Looking back from the perspective of years or decades from now, this Nobel will likely mark a turning point. The moment quantum computing transitioned from exotic research topic to recognized technology. Before, it was speculative. After, it was Nobel-worthy. That shift in perception matters for funding, recruitment, public understanding, everything that determines whether a technology flourishes or withers. The laureates themselves seem bemused by the attention. Clark mentioned he never imagined this work would be prize-worthy. Martini's emphasized the contributions of colleagues and students. Devereux focused on the future, on what quantum computers might achieve rather than what they've done. Humble responses from people who've spent careers pushing boundaries and suddenly find themselves celebrated for it. And those boundaries keep moving. The circuits they studied had microamps of current, nanowatts of power. Modern qubits are even smaller, even more precisely controlled. The principles remain the same. Build a quantum system, isolate it from noise, manipulate it carefully, extract information from it, but the execution has improved by orders of magnitude. What took specialized labs with custom equipment in the 80s can now be done with commercially available components, at least in some cases. This democratization matters. When only a few groups worldwide can perform experiments, progress is slow. When many groups can contribute, when students can work on real quantum systems instead of just reading about them, the pace accelerates. We're seeing this now. Quantum computing courses appear in university curricula. Quantum programming languages exist. Cloud-based access to quantum computers lets researchers worldwide run experiments without building hardware. The Nobel Prize caps 4 decades of development from initial demonstration to working technology. But it's not an endpoint. It's recognition that the foundation is solid, that building higher makes sense. The real breakthrough is the applications that change daily life, remain ahead. Quantum computers that design drugs, quantum sensors that diagnose disease, quantum communication networks that can't be intercepted. These aren't guaranteed, but they're possible now in a way they weren't before 3 scientists proved that quantum mechanics works at scales we can engineer. UAP disclosure accelerates the age of truth. Something shifted in September. Not a single dramatic announcement or undeniable piece of evidence. Rather, accumulation of official statements, congressional hearings, documentary releases and whistleblower testimonies that collectively crossed a threshold. The conversation about unidentified anomalous phenomena isn't fringe anymore. It's mainstream, institutional, and accelerating in ways that suggest either genuine disclosure is approaching, or we're witnessing the most elaborate information operation in modern history. September 9th. The House Oversight Committee's task force on the declassification of federal secrets held a hearing titled Restoring Public Trust Through UAP Transparency and Whistleblower Protection. Note the framing. Not whether UAPs exist or what they are, but how to protect people coming forward with information about them. The hearing assumed phenomenon and focused on process, a subtle but significant shift in how official bodies approach the topic. Witnesses included Chief Alexandra Wiggins, who spoke about aviation and maritime safety concerns when crews observe objects maneuvering in ways that don't match known profiles near ships and aircraft. His testimony wasn't about aliens or speculation. It was operational, practical, focused on sensor data and chain of custody procedures for recordings. The kind of testimony that's hard to dismiss because it doesn't make extraordinary claims, just describes extraordinary observations. Jeffrey Nucitelli, Air Force veteran, emphasized whistleblower protection. Transparency is the foundation of truth, he said. Without it, witnesses like us are dismissed. Many stay silent out of fear for their careers, reputations, and safety of their families. Protect them, and you will embolden others to join this cause. The implication being that significant information exists, but people won't come forward without legal safeguards against retaliation. This hearing came after months of pressure from a small group of congressional representatives who've made UAP transparency a priority. Representatives Tim Burchett and Anna Paulina Luna introduced legislation that would codify specific protections for whistleblowers disclosing information about government funding for UAP research. The bill was referred to multiple committees: Oversight, Armed Services, Intelligence, indicating the topic touches numerous jurisdictions and interests. The legislation matters less for its specific provisions than for what it represents. Elected officials on record acting as if UAP research is real, and government secrecy around it is a problem requiring legislative remedy. This isn't a joke or publicity stunt. It's policy process, slow and bureaucratic but moving forward. Then came the age of disclosure. Documentary released November 21st on Amazon Prime with limited theatrical release for Oscar qualification. Director Dan Farrar spent 3 years making it in secrecy, interviewing 34 former and current government officials who claim the United States has been working to capture UFOs since 1947. The film's narrator is Lou Elizondo, former Department of Defense official who ran what he describes as a UAP investigation program before resigning in protest over excessive secrecy. Elizondo's been a central figure in recent disclosure efforts. His credibility is both asset and liability. Asset because his documented government service and security clearances suggest he had access to classified programs. Liability because he's now deeply involved in UFO advocacy, which raises questions about objectivity and motivation. Critics accuse him of mixing facts with speculation. Supporters say he's trying to thread an impossible needle, revealing what he can without violating classification laws that carry severe penalties. The documentary features high-ranking officials making remarkable claims. Senator Marco Rubio, Senator Kirsten Gillibrand, both on record discussing UAP legislation and investigations. Jay Stratton, former director of the UAP task force, claiming there's a race among governments to reverse engineer alien technology. The first country that cracks the code on this technology will be the leader for years to come, he said. That statement alone, if taken seriously, reframes UAPs from curiosity to strategic priority. Reviews were mixed. IndieWire called it the most convincing argument you can make without showing any actual evidence. The Guardian noted it presents testimonies that need to be backed up with evidence that hasn't been provided. Critics pointed out that everything in the film relies on people saying things rather than showing things. No physical evidence, no classified documents, no hardware, just voices claiming knowledge. But consider what we're watching. Senators, former intelligence officials, military personnel, all going on camera to discuss UAP programs as if they're real. Either they're correct or they're all mistaken, or they're deliberately spreading misinformation. Each possibility is wild in its own way. If they're correct, we're in the early stages of confirmation that non-human intelligence interacts with Earth. If they're mistaken, our national security apparatus has spectacularly failed at basic information vetting. If it's misinformation, the question becomes why and who benefits. Colonel Carl Nell appeared at Rice University's archives of the Impossible Conference in 2025 with something extraordinary, a roadmap. 5 phases of disclosure. Phase 1, prove UAPs exist, marked as 2024. Phase 2 through 5 stretch to 2034 and beyond, culminating in engage with non-human intelligence. The presentation was structured like a corporate strategy document, PowerPoint slides with timelines and objectives. Think about the absurdity for a moment. A retired Army intelligence officer and Pentagon UAP advisor standing at a major university presenting a multi-decade plan for humanity to prepare for contact with non-human intelligence. This isn't a science fiction convention, it's a venue for serious academic discussion. And the presentation wasn't framed as speculation. It was framed as planning, as if the outcome is certain and the only question is managing the transition. Nell's timeline suggests we're in the early phases. Proving UAPs exist, essentially complete according to the framework. The next phases involve understanding what they are, how they work, establishing communication protocols, and eventually formal engagement. 2034 is less than a decade away. If this roadmap is remotely accurate, children in elementary school right now will graduate high school into a world where non-human intelligence is acknowledged reality rather than speculation. But roadmaps and claims aren't evidence. The persistent frustration for both believers and skeptics is the lack of physical proof accessible to independent analysis. Testimony is abundant. Radar data exists but remains mostly classified. Videos exist. The Navy released 3 in recent years, but they show objects behaving strangely without proving what they are. Photos exist, but image analysis can only go so far. What's missing is hardware, a piece of something that definitively didn't come from Earth or human technology. This is where the leaked Yemen incident becomes interesting. Video emerged showing what appears to be a US missile striking an unidentified object off the coast of Yemen in 2024. The footage came via leak, not official disclosure. Representative Burleson and others questioned why the public learned about it through leaks rather than government transparency. If the military is engaging unknown objects with weapons, that seems like information citizens deserve. The Pentagon's response has been carefully calibrated. They acknowledge UAPs are real as in unidentified objects are observed. They've established the All-Domain Anomaly Resolution Office, AARO, to investigate reports. But they maintain that no evidence suggests non-human intelligence or technology beyond human capability. This creates a strange situation where officials simultaneously confirm the phenomenon exists and deny it's extraordinary. Critics like Christopher Mellon, former Deputy Assistant Secretary of Defense for Intelligence, argue the Pentagon is dragging its feet. After the Navy videos were released, the intelligence community reclassified almost everything concerning UAP, slowing disclosure to a trickle. Mellon helped leak those original videos and has become an advocate for transparency. His argument is that thousands of UAP reports and videos exist, many no more sensitive than the 3 made public, but they remain locked away without justification. The classification system is where government secrecy becomes most frustrating for researchers and public alike. Anything can be classified for almost any reason. Once classified, it's illegal to discuss specifics even if the information seems innocuous. This creates a black hole where evidence might exist but can't be examined or even acknowledged. Whistleblowers risk prosecution. Officials who want transparency face legal constraints. The system perpetuates itself. Yet information keeps emerging. The Immaculate Constellation report leaked to journalists allegedly describes a UAP observation program far more extensive than publicly acknowledged. multiple classified briefings have occurred for congressional members, who emerge with mixed reactions ranging from dismissive to deeply concerned. Some representatives report being blocked from accessing information even with appropriate clearances. Others claim what they've seen convinces them this is serious. The National Archives now has a deadline. September 30th, 2025, all federal agencies must identify and transfer publicly releasable UAP records to the new Unidentified Anomalous Phenomena Records Collection. This mandate, part of the 2024 National Defense Authorization Act, creates a formal mechanism for disclosure. Whether agencies comply meaningfully or engage in minimal compliance is the question. What's notable is the institutional framework being built. Not just hearings, but task forces. Not just reports, but dedicated offices. Not just requests, but mandates with deadlines and penalties. This level of bureaucratic machinery doesn't get deployed for topics considered frivolous. Either this represents serious concern about a genuine phenomenon, or it's elaborate theatre. Both possibilities are unsettling. The international dimension adds complexity. The documentary and hearings focus on US programs, but other countries have their own UAP encounters and research efforts. France has Guy Pan studying reports for decades. Chile has CFAA maintaining detailed records. Russia presumably has programs that remain classified. China likewise. If this is a global phenomenon, it has implications beyond national security into questions about planetary security, assuming the objects represent something non-human. Or perhaps they're all human technology, just not openly acknowledged. Secret aerospace programs. Breakthrough propulsion systems kept classified for strategic advantage. This would explain the government's reluctance to discuss details. You don't advertise your most advanced capabilities, but it requires believing that multiple countries independently developed aircraft that vastly exceed publicly known performance, and all somehow kept it secret despite normal leaks and intelligence gathering. The performance characteristics described in credible reports are genuinely bizarre. Objects accelerating instantly from hover to hypersonic speeds, right-angle turns at velocities that should produce thousands of Gs, transmedium capability, moving seamlessly between air and water. No visible propulsion, no exhaust, no sonic booms. If this is human technology, it represents physics breakthroughs that would revolutionize every aspect of transportation and energy. Keeping that secret would be challenging and arguably counterproductive given the global problems such technology could solve. Which brings us back to non-human intelligence as explanation. If not human tech, then what? Extraterrestrial visitors from other star systems, ultra-terrestrial intelligence that evolved here but separately from humans, interdimensional travelers from parallel realities, future humans with time travel capability. Each explanation sounds like science fiction, yet each has been seriously proposed by researchers trying to make sense of the data. The extraterrestrial hypothesis is most popular because it's conceptually straightforward. Advanced civilizations elsewhere in the universe developed interstellar travel and periodically visit Earth. The distances are enormous but perhaps manageable with physics we don't understand yet. Motivation could be scientific curiosity, the way we study other species without necessarily interfering, or maybe interference happens and we just don't recognize it. Ultra-terrestrial theories suggest intelligence evolved on Earth, long before humans or alongside humans, but remained hidden, perhaps underwater civilizations in ocean depths we've barely explored, perhaps in cave systems, perhaps they're simply good at avoiding detection. This feels like fantasy until you consider how much of Earth remains unexplored. We've mapped the ocean floor at lower resolution than we've mapped Mars. Who knows what's down there? Interdimensional theories borrow from physics ideas about parallel universes and extra dimensions beyond the four we experience. If other dimensional spaces exist, perhaps they're inhabited. Perhaps whatever lives there can sometimes interact with our dimension. This conveniently explains why UAPs seem to appear and disappear, why they violate our physics expectations. They're not breaking our rules, they're following different ones from their native dimension. Time travel theories are particularly brain-breaking. If humans develop time travel in the future, they could visit now. Future humans studying past humans, their own ancestors. This creates causality problems philosophers and physicists love arguing about. It also potentially explains why UAPs often appear near military installations and during significant historical events. They're tourists or researchers from our own future. Each theory has problems. Extraterrestrial travel faces the enormous distances of interstellar space. Ultra-terrestrials face the question of why they've remained hidden so effectively. Interdimensional beings require accepting physics that's speculative at best. Time travelers create paradoxes. None fit perfectly, which might mean all are wrong and the truth is something we haven't imagined yet. Or it means the phenomenon is more complex than any single explanation captures. Maybe multiple things are happening. Human secret technology accounts for some sightings. Natural phenomena misidentified for others. Genuine anomalies requiring new explanations for the remainder. Trying to force everything into one box might be the fundamental error. The disclosure movement's central frustration is being stuck between these possibilities without sufficient evidence to resolve anything. Testimony is plentiful, but testimony is just people saying things. What's needed is physical evidence, analysed openly with results published where the scientific community can critique methodology and review conclusions. Until that happens, we're trapped in endless argument. Yet the momentum feels different now. Congressional hearings that treat UAPs as real rather than joke, legislation creating frameworks for disclosure, documentary films with high production values interviewing credible officials, roadmaps from military insiders projecting timelines for contact. Either we're approaching genuine revelation, or we're watching sophisticated psychological operations unfold. Both prospects are fascinating and concerning in different ways. The 2034 timeline Nell presented isn't arbitrary. It aligns roughly with other predictive frameworks floating in UAP research communities. Some researchers point to increasing sighting rates. Others note escalating official acknowledgement. Still others reference alleged communications or contacts claiming specific timeframes. Conspiracy thinking at its finest, connecting dots that might be random into patterns that might be illusory. But if the pattern is real, if disclosure is genuinely accelerating towards some culmination point, the next decade will be extraordinary. Not because aliens will land on the White House lawn necessarily, but because the social, political, and philosophical implications of confirmed non-human intelligence would reshape human civilization's self-understanding completely. We wouldn't be alone. We wouldn't be the pinnacle of intelligence in the universe. Our religions, our philosophies, our sciences, all would need reconsidering in that context. And if it's all smoke with no fire, if disclosure movement represents misunderstanding or misinformation or wishful thinking, then we're watching a case study in how modern information ecosystems can create and sustain elaborate narratives despite absence of physical proof. That's important too, understanding how beliefs form and spread, how authority and testimony interact with evidence and skepticism. Either way, something significant is happening. The question is what? Space's hidden secrets emerge. While debates rage about artificial intelligence controlling governments and quantum computers breaking reality, astronomers keep discovering the universe is stranger than the conspiracy theories suggest. October 2025 brought a cascade of findings that quietly reshape our understanding of planetary formation, stellar evolution, and the very structure of our own planet. No aliens required, though the implications for where life might exist and how Earth became habitable are profound. Deep inside our planet, nearly 2,000 miles down, scientists found remnants of the proto-Earth that existed before the Moon, forming a collision. This discovery, announced less than a week ago, answers questions geologists have been asking for decades, while raising new ones about how planets evolve after catastrophic impacts. The prevailing theory of lunar formation involves a Mars-sized object nicknamed Theia, slamming into early Earth roughly 4.5 billion years ago. The impact vaporized massive amounts of material. Some coalesced into the Moon, the rest reformed as Earth, thoroughly mixed and homogenized by the violence of collision. That's what models predicted. Complete blending, no remnants of the original bodies. But seismic data never quite matched that prediction. Deep in the mantle, two massive anomalies exist. The African blob and the Pacific blob, technical names pending. These are regions where seismic waves slow down, indicating different composition or temperature than surrounding mantle. They are enormous, each larger than the Moon, sitting at the core mantle boundary. The new research suggests these blobs are pieces of Theia, not fully mixed into Earth during the collision, but sunk to the bottom of the mantle where they've remained for billions of years. Chemical analysis of volcanic rocks, which sometimes carry material from deep mantle regions, shows unusual isotope ratios consistent with material that formed elsewhere in the solar system before accreting into Earth. Think about the implications. Inside our planet sits substantial mass from another world. Proto-Earth and Theia didn't fully merge. They're still partially distinct, layered like oil and water, but at planetary scale. This affects everything from how Earth's magnetic field generates to why volcanic hotspots exist where they do. Those blobs might be chemically distinct enough to influence mantle convection patterns, which drive plate tectonics, which shapes continents and ocean basins, which determines climate. If remnants of planetary collisions persist inside planets rather than homogenizing completely, every rocky world in the universe potentially contains a geological record of its violent formation. Core samples from Mars or Venus, if we ever obtain them, might reveal similar layered structures. Understanding these internal architectures becomes crucial for understanding planetary evolution. The Moon itself benefits from this revelation. If Theia material is inside Earth, and the Moon formed from impact debris, the Moon likely contains mixed material from both bodies. Lunar samples already showed chemical similarities to Earth that seemed too close for separate origins. Now we understand why. The Moon is made from both Earth and Theia, thoroughly blended during the impact, while Earth kept some unmixed Theia in its depths. Elsewhere in the solar system, James Webb Space Telescope scored another victory by identifying a red supergiant star that later exploded as a supernova. This solves what astronomers call the red supergiant problem. Theory predicts these massive stars should explode as Type II supernovae, but observations often fail to detect them right before the explosion. They seem to disappear in the years leading up to their death, hidden by dust or dimmed by some process we didn't understand. Webb's infrared vision can pierce dust that blocks visible light. By observing in infrared wavelengths, it caught the supergiant before it exploded, confirming it was there despite being invisible to other telescopes. The star was shrouded in material it had shed in its final years, creating a dusty cocoon that hid it from view. When it exploded, the outburst cleared away the dust, revealing what had been there all along. This matters because understanding stellar evolution requires catching stars at every stage. We've seen plenty of supernovae and their aftermaths. We've studied many red supergiants that haven't exploded yet, but catching one in transition, the crucial moments before detonation, has been frustratingly rare. Each observation helps refine models of how massive stars die and what they leave behind. Supernova remnants seed the galaxy with heavy elements. Carbon, oxygen, nitrogen, everything heavier than hydrogen and helium, is forged in stellar cores or during explosive deaths. We are made of star stuff, as Carl Sagan famously noted. Understanding how stars create and distribute those elements helps explain how planets like Earth acquired the building blocks for life. Speaking of building blocks, Saturn's moon Enceladus continues revealing itself as one of the most promising locations for life beyond Earth. Fresh analysis of Cassini data, the spacecraft that studied Saturn until 2017, found complex organic molecules in the water geysers shooting from Enceladus's south pole. Not just simple carbon compounds, but large complex structures that on Earth are associated with biological processes. The molecules were detected in Saturn's E-ring, which is constantly replenished by Enceladus's geysers. This means the complex organics aren't products of long exposure to space radiation, but come directly from the subsurface ocean. Whatever chemical processes are happening under Enceladus's ice shell, they're producing the ingredients of life. Frank Postberg, one of the researchers, emphasized this point. These molecules prove that complex organics Cassini detected aren't just a product of long exposure to space, but are readily available in Enceladus's ocean. The ocean is actively producing or maintaining these compounds. Whether biological processes are involved remains unknown, but the chemistry is promising. Enceladus checks many boxes for habitability. Liquid water ocean confirmed by gravitational measurements and direct observation of geyser eruptions. Energy source from tidal heating as Saturn's gravity flexes the moon. Complex organic chemistry. Rock-water interface at the ocean floor where hydrothermal vents might exist. On Earth, similar environments support thriving ecosystems independent of sunlight. The case for returning to Enceladus grows stronger with each analysis of old data and each new understanding of what makes environments habitable. A dedicated mission could fly through the geyser plumes, sampling material directly from the ocean without landing or drilling. Instruments exist that could detect biosignatures if life is present. Whether space agencies will fund such a mission is a question of budget priorities and political will. Meanwhile, closer to home, Mars continues playing coy about whether it ever hosted life. Perseverance rover found mudstones in Jezero crater, containing organic carbon and unusual textures that some researchers interpret as possible biosignatures. The leopard spot patterns in the rocks resemble features that on Earth are associated with microbial activity. But possible biosignatures aren't confirmed biosignatures. Abiotic processes, chemistry without biology, can produce similar patterns. Definitively proving biological origin requires more analysis than a rover can perform on Mars. The samples Perseverance has been caching are intended for eventual return to Earth, where laboratory analysis could settle the question, but that return mission faces uncertain funding and timeline challenges. What's clear is that ancient Mars was wetter. Jezero crater was once a lake fed by rivers. The rocks Perseverance studies formed in that aqueous environment. Whether life emerged in those waters is unknown, but conditions appear to have been suitable. Water, organic carbon, energy sources from volcanism and chemical reactions, all the prerequisites were present. The search for life beyond Earth has shifted from asking if conditions allow it to asking where to look and how to recognize it. Every new habitat we examine expands the range of conditions life might tolerate. Extremophiles on Earth survive in acid, in ice, in boiling water, in crushing pressures, in complete darkness, in environments that would quickly kill humans. Each discovery of terrestrial life in extreme conditions widens the search parameters for extraterrestrial life. But space delivered stranger discoveries too. Astronomers detected the most distant and energetic odd radio circle ever found, nearly 10 billion light-years away. Odd radio circles are exactly what they sound like. Mysterious circular structures visible only in radio wavelengths. They're enormous, hundreds of thousands of light-years across, and nobody is entirely sure what causes them. The leading theory involves shock waves from massive galactic events, perhaps collisions between galaxies or outbursts from supermassive black holes. But the physics is still being worked out. Finding one this distant, meaning we're seeing it as it existed 10 billion years ago when the universe was much younger, provides clues about when these structures started forming and what conditions produced them. Then there's the rogue black hole actively feeding despite being displaced from its galaxy's centre. Black holes typically lurk in galactic cores, growing fat on gas and stars that venture too close. Finding one almost a kiloparsec, 3,000 light-years from where it should be and actively producing radio jets defies expectations. How did it get displaced? What's feeding it out in the relative emptiness between galactic structures? One possibility is a galactic collision kicked it out. When galaxies merge, their central black holes can interact gravitationally in ways that sometimes eject one or both from the merge system. But ejected black holes usually aren't actively feeding. They're isolated, starving in the void. This one found something to eat, or it brought its meal with it. A captured gas cloud, perhaps. The discovery highlights how much happens in the universe that we rarely witness. Black holes feeding far from galactic centres, stars exploding in dusty cocoons, ancient planetary collision remnants preserved in mantle depths, organic chemistry brewing in subsurface oceans, radio structures spanning galaxy clusters. Each observation pushes boundaries of what we thought possible. Titan, Saturn's largest moon, broke chemistry rules. Scientists announced that incompatible substances mix on Titan's surface despite the principle that, like dissolves like. At Titan's frigid temperatures, negative 179 degrees Celsius, chemistry behaves differently. Compounds that couldn't coexist in Earth conditions form stable mixtures. This matters for astrobiology because it means alien biochemistry might use solvents and reactions that seem impossible in Earth terms. Liquid methane on Titan could support chemistry leading to life, just not life as we know it. The phrase life as we know it gets overused, but here it's precise. Carbon-based water-solvent life dominates Earth. But carbon can work with other solvents. Silicon might substitute in some contexts. The possibilities expand when you consider environments with completely different temperature and pressure regimes. October also brought the dual comet spectacle as Lemon and Swan reached closest approach to Earth. Both brightened to naked-eye visibility for observers with dark skies, rare treats for amateur astronomers. Comets are time capsules, icy bodies from the solar system's formation that spent billions of years in deep freeze before gravitational perturbations sent them sunward. Each comet carries information about conditions in the early solar system. The ice preserves ancient chemistry. The dust contains pre-solar grains, material that predates the sun's formation. By studying comets, we study the raw materials from which everything in our solar system formed, and occasionally we get to watch them put on a show as solar heating vaporizes their ices, creating glowing comas and tails. Lemon was discovered in January by the Mount Lemmon survey, a mile-sized ball of ice and rock dropping in from the Oort cloud for a brief visit. By month's end it peaked around 8th magnitude, comparable to Messier galaxies accessible to small telescopes. Swan followed a similar trajectory, approaching even closer at 24 million miles. Having two bright comets simultaneously is unusual. Most years see none visible without optical aid. Some years see one. Two at once, both reasonably bright, provides opportunities for comparative study and spectacular images as astrophotographers captured both in single frames. The science of comets intersects with the search for life's origins. Some theories propose that comets delivered significant amounts of water to early Earth, along with organic compounds. If true, comets weren't just frozen debris, but crucial contributors to making Earth habitable. Every comet we study helps test that hypothesis. Discoveries accelerate as our instruments improve. James Webb is barely into its operational lifetime and already revolutionizing multiple fields. Next-generation ground-based telescopes coming online in the next few years will push sensitivity and resolution further. Space missions to Europa and Enceladus could launch this decade. Mars sample return, if funded, could bring definitive answers about Martian life. The universe is revealing itself layer by layer. Each answer spawns new questions. Finding proto-Earth material in the mantle raises questions about how planetary interiors evolve. Detecting complex organics on Enceladus raises questions about what chemistry exists in that ocean. Observing distant odd radio circles raises questions about early universe energetics. Every field of astronomy and planetary science is simultaneously advancing, and the pace keeps increasing. Data accumulates faster than scientists can analyze it. Archives hold discoveries waiting for someone to notice them. New instruments plan observations that will reveal phenomena we haven't imagined yet. Within our lifetimes, we might answer whether life exists elsewhere, whether our solar system is typical or unusual, how galaxies form and evolve, what dark matter and dark energy actually are. Or we might answer some questions while uncovering deeper mysteries. Science often works that way. You solve one puzzle and find two more behind it, but each solved puzzle expands human knowledge. Each answered question reveals more about the cosmos and our place in it. That journey of discovery continues, accelerating, leading toward understandings we can barely glimpse from our current position. The universe is vast, ancient, and full of wonders that dwarf human imagination. We're privileged to live in an era where technology allows us to study it in detail, to peer back to cosmic dawn, to analyze atmospheres of distant worlds, to map the internal structure of our own planet. What we're learning transforms not just astronomy, but our fundamental understanding of what's possible, where we came from, and what else might be out there. AI's October revolution. The artificial intelligence landscape shifted dramatically this month through a combination of hardware deals, algorithmic breakthroughs, and deployments at scale that collectively signal the technology is transitioning from experimental to foundational. Three announcements in particular deserve attention because they illuminate where AI development is heading and who's positioning to control that future. First, OpenAI and AMD sealed a multi-billion-dollar agreement that analysts are calling the opening salvo in an AI infrastructure arms race. The deal commits AMD to supplying 6 gigawatts of computing power through their Instinct series chips, beginning with the MI450 GPUs in late 2026. 6 gigawatts is difficult to conceptualize, but consider that most data centers consume tens of megawatts. This represents enough computing capacity to power multiple massive AI training facilities. The financial structure is unusual. Beyond hardware purchases, OpenAI receives warrants on up to 10% of AMD shares. This equity arrangement ties the company's fortunes together in ways that transcend normal supplier-customer relationships. AMD's stock surged 38% on the announcement. Barclays projects over $100 billion in revenue from the partnership within 5 years. These numbers suggest the market believes we're witnessing formation of critical infrastructure for the next technology era. Why does this matter beyond business headlines? Because AI development has hit a bottleneck, and that bottleneck is compute. Training frontier models requires thousands of specialized processors running for months. Each generation of models demands more computation than the last. GPT-3 needed hundreds of petaflop days. GPT-4 required orders of magnitude more. The next generation will require even more. Without sufficient hardware, progress stalls. NVIDIA currently dominates this market. Their H100 and newer chips power most major AI training. That monopoly creates problems, supply constraints, price leverage. Single point of failure risks. AMD's emergence as credible alternative reshapes the landscape. Competition typically accelerates innovation while reducing costs. OpenAI betting this heavily on AMD signals confidence that the chips will perform and deliver on time. But the deal represents more than diversification. It's about securing guaranteed access to compute at a scale that enables continuing model development. As AI systems grow more capable, their appetites for computation grow exponentially. Planning years ahead for hardware procurement becomes essential. OpenAI is essentially locking in future capacity, ensuring they won't be compute limited when competitors might be. Meanwhile, Anthropic, OpenAI's primary rival, announced its largest enterprise deployment ever. 470,000 Deloitte employees across 150 countries now have access to Claude. This isn't a pilot program, it's integration at massive scale into daily workflows of a Big Four consulting firm. The partnership involves significant financial and engineering commitments from both companies. What makes this newsworthy is what it represents about AI maturity. Moving from experimental tools that early adopters play with to core business infrastructure that 500,000 employees rely on daily requires reliability, security, compliance with regulations, integration with existing systems, training programs, support infrastructure. This deployment demonstrates that enterprise AI has crossed that threshold for at least some use cases. Deloitte presumably conducted extensive evaluation before committing. Consulting firms are professionally skeptical and risk-averse. They need tools that enhance employee productivity without creating liability or security vulnerabilities. That they chose Claude and deployed it this broadly suggests confidence in the technology's readiness. It also signals to other enterprises that adoption is becoming standard rather than experimental. The competitive dynamics are fascinating. OpenAI dominates consumer AI through ChatGPT's 800 million weekly active users, a number that grew by 100 million in a single month. But Anthropic is winning major enterprise contracts, positioning Claude as the reliable choice for businesses that prioritize safety and interpretability. Different strategies for different markets, both potentially viable. Then there's the infrastructure layer. IBM partnered with Grok to integrate their inference acceleration technology into Watson Orchestrate. Grok's language processing units, LPUs, deliver over 5 times faster inference than traditional GPU systems at lower cost. Inference is what happens when you use a trained model, as opposed to training which is building the model initially. Improving inference speed and efficiency matters enormously for real-world deployment. Healthcare applications were highlighted. Hospital systems receive thousands of complex patient questions simultaneously. Fast inference means AI agents can analyze information and provide accurate answers in real time. Similar benefits apply across industries. HR systems, customer service, financial analysis. Anywhere rapid response matters. IBM bringing this capability to their enterprise clients accelerates practical AI adoption. The quantum computing connection shouldn't be missed. IBM's also pushing quantum AI integration. Grok's custom LPU architecture demonstrates that specialized hardware designed specifically for AI workloads dramatically outperforms general-purpose chips. This lesson applies to quantum systems too. As quantum computers mature, quantum AI accelerators might provide advantages that classical systems, even specialized ones, cannot match. But hardware advances mean little without algorithmic progress. October saw announcements of models achieving human-level performance or better on increasingly difficult benchmarks. GPT-5, OpenAI's next-generation model, demonstrated 94.6% accuracy on AI-Me 2025, a mathematics competition where typical human performance is much lower. The model handles text, images, audio, and video seamlessly in unified systems. Benchmark. Performance improvements are controversial in AI research. Critics argue that benchmarks get gamed, that models memorize training data, including test sets, that narrow task performance doesn't indicate general intelligence. All valid concerns. But the trend is undeniable. Each model generation handles tasks that previous generations failed at. The capabilities expand even as debates continue about what those capabilities mean. Microsoft's Copilot Studio 2025. Wave 2 launch provided tools for businesses to create custom AI agents without coding. Multi-agent orchestration means different specialized agents can coordinate to solve complex problems. One agent handles scheduling, another analyzes documents, a third manages communications. They work together, passing information and results, accomplishing tasks that would be difficult for any single system. This no-code approach democratizes AI development. Small businesses without engineering teams can deploy AI solutions tailored to their needs. The barrier to entry drops from requiring machine learning expertise to requiring understanding of your business processes. That's still substantial but manageable for many more organizations. As tools improve and simplify, adoption accelerates. Google rolled out Gemini for Home, integrating AI throughout smart home ecosystems. Natural language control, predictive notifications, learning user preferences and patterns. The vision is ambient intelligence, AI that fades into the background while continuously assisting. Your home anticipates your needs. The thermostat adjusts before you feel uncomfortable. The lights adapt to activity and time of day. Shopping lists update automatically as supplies run low. Whether this vision is appealing or dystopian depends on perspective. Convenience versus surveillance. Assistance versus dependence, control versus automation. These tensions run through all AI deployment but become visceral when the technology enters homes and monitors daily life. Google argues that processing happens locally on device for privacy. Critics worry about data collection regardless of stated policies. The regulatory environment struggled to keep pace. AI safety discussions intensified after Yoshua Bengio, deep learning pioneer and Turing Award winner, warned that humanity could face extinction within a decade if AI development proceeds without adequate safeguards. Not hyperbole from a fringe figure, but considered opinion from someone who helped create the field. He suggested that advanced systems might prioritize self-preservation over human interests. This existential risk framing remains controversial. Many researchers think it distracts from present harms, bias, misinformation, job displacement, surveillance. Others believe both near-term and long-term risks deserve attention. The debate is fierce and unlikely to resolve soon, but it's moved from purely academic to policy relevant as governments consider how to regulate increasingly powerful AI systems. Europe continued developing its AI sovereignty strategy. Apertus, Switzerland's first large-scale open-source language model, launched in September, trained on 15 trillion tokens across over 1,000 languages, with 40% non-English data, including Swiss German and Romansh. The model is completely transparent, architecture, training data, model weights, development process all publicly accessible under permissive license. This contrasts sharply with closed models from major tech companies. OpenAI, despite the name, no longer publishes model details. Anthropic releases some information but keeps core training methods proprietary. Google and Microsoft likewise guard their AI developments closely. Open-source alternatives provide options for organizations concerned about vendor lock-in or sovereignty issues. Switzerland positioning itself as an AI hub through open development could influence European tech policy more broadly. The continent has struggled to compete with American and Chinese AI companies. Building open infrastructure that anyone can use and build upon might be a viable alternative strategy. Instead of creating European champions to compete with ChatGPT, enable anyone to create competitive tools using shared foundations. The UK signed a tech prosperity deal with the United States, securing over $31 billion in commitments from Microsoft, Google, Nvidia, OpenAI, and others for data centers and AI infrastructure. An AI growth zone in northeast England promises tens of thousands of skilled jobs. These investments indicate where companies expect AI development to concentrate geographically, chasing talent, energy resources, regulatory environments that enable experimentation. Energy deserves special attention. Training large AI models consumes enormous electricity. Data centers require constant cooling. The environmental impact is significant and growing. 6 gigawatts of computing capacity doesn't just require chips, it requires power generation and distribution capable of supplying that much energy continuously. Renewable sources become essential not just for environmental reasons, but for cost and sustainability. Microsoft is committed to running data centers on renewable energy. Google has similar pledges, but matching consumption with generation, especially as demand grows, challenges even well-funded companies. Some facilities locate near hydroelectric or geothermal sources. Others purchase renewable energy credits. The tension between AI's hunger for computation and climate commitments is real and increasing. Costs are dropping though. Running advanced models is over 280 times cheaper than late 2022. Efficiency improvements in hardware and algorithms reduced expenses dramatically. What cost millions to train now costs tens of thousands. Inference costs dropped even more precipitously. This economic shift enables applications that weren't viable before. When running a query costs fractions of a cent instead of dollars, new use cases become possible. Adoption statistics from October show 78% of organizations now use AI, up from 55% last year. 71% of top companies employ generative AI for product innovation. These aren't experimental side projects anymore. They're core to business strategy and operations. The shift happened fast, accelerating through 2024 and into 2025. Multimodal AI advances received significant attention. Systems that integrate text, images, audio, video provide richer interaction than text-only models. You can show the AI a photograph and ask questions about it, record audio and get transcription plus analysis, upload video for summarization and content extraction. The market for multimodal AI reached $2.27 billion this year with projections for rapid growth. Synthetic data emerged as partial solution to privacy and scarcity challenges. Training AI requires massive data sets, but data has owners, privacy implications, potential biases. Synthetic data, artificially generated to match statistical properties of real data without containing actual information about real people, offers a way forward. Models trained on synthetic data can achieve comparable performance to those trained on real data in some contexts. The synthetic data market, forecasted to rise from $500 million in 2025, demonstrates commercial viability. Companies offer services generating synthetic datasets for specific domains, healthcare data for training medical AI without violating patient privacy, financial transactions for fraud detection without exposing real account information. The technique has limitations but fills important gaps. But October also brought concerning revelations. Researchers discovered that a handful of poisoned training documents can backdoor even the largest AI systems. Malicious actors could inject data into training sets that create hidden vulnerabilities. The model performs normally on most inputs but misbehaves in specific circumstances. Detecting these backdoors is extremely difficult because training datasets contain billions of documents. Finding a few malicious ones is needle-in-haystack territory. This has major security implications. If AI systems make critical decisions in healthcare, finance, infrastructure, transportation, backdoors could cause catastrophic failures. Even if unintentional data contamination rather than deliberate attack, the risk exists. Validating training data becomes essential but challenging given data scales involved. Solutions are being developed, but the problem highlights AI security challenges that will only grow as systems become more capable and consequential. Samsung announced a 7 million parameter model outperforming giants thousands of times larger on specific tasks. This seems impossible. Larger models should always beat smaller ones, but the result demonstrates that architecture and training methods matter as much as size. Clever design and efficient use of parameters can achieve surprising results. This bodes well for deploying AI on resource-constrained devices like phones and embedded systems. The pattern across all these developments points toward AI transitioning from novelty to infrastructure. The conversations are less about whether AI works and more about how to deploy it reliably, ethically, securely. The infrastructure deals lock in compute capacity. The enterprise deployments demonstrate viability. The algorithmic improvements show continuing progress. The regulatory debates acknowledge AI's growing impact on society. We're watching the early stages of a major technological shift. Not as dramatic as the internet's arrival, perhaps, but potentially as transformative. AI touches more aspects of life and business than any previous computing paradigm. It's not a single application or platform. It's a capability that enhances or replaces cognitive work across domains. Whether this is good depends on how it's managed. The benefits are obvious: increased productivity, enhanced capabilities, solutions to problems previously intractable. The risks are equally obvious: job displacement, surveillance, misinformation, concentration of power, potential for misuse. Navigating between maximizing benefits and minimizing harms will define technology policy for the next decade. The conspiracy spiral: what's real in 2025? The boundary between conspiracy theory and legitimate questioning has never been blurrier. When elected officials testify about government UAP programs, when quantum computers demonstrate capabilities that sound like science fiction, when AI systems produce outputs indistinguishable from human writing, the landscape of plausibility shifts. What seemed absurd yesterday becomes possible today. And into that uncertainty, conspiracy theories flourish with unprecedented vigour. October 2025 brought fresh research on how conspiracy beliefs spread and why they persist despite contradicting evidence. A study following the Trump assassination attempt in July 2024 provides rare real-time data on conspiracy formation. Within hours of the shooting, researchers deployed surveys to capture how information and misinformation propagated through the population. The results are sobering. 95% of respondents heard about the assassination attempt quickly, which is expected for major news. But 41% had heard the right-leaning conspiracy theory that Democrats orchestrated the shooting, and 53% heard the left-leaning theory that Republicans staged it to boost Trump's popularity. Within days, conspiracy theories achieved nearly the same reach as factual reporting. More troubling, a substantial fraction believed these theories. Of those who heard the Democratic plot theory, 13% considered it very likely and 16% somewhat likely. For the Republican staging theory, 12% very likely and 17% somewhat likely. Nearly 30% of people exposed to these conspiracies found them credible despite zero evidence supporting either. David Laser, the Northeastern University professor who conducted the research, emphasizes how quickly misinformation spreads and how many people accept it. The vacuum of information immediately following major events gets filled with speculation, rumor, and conspiracy. People encounter these narratives through social media, messaging apps, friends, family. Repetition creates familiarity. Familiarity breeds credibility. This dynamic explains why conspiracy theories have become so prevalent in 2025. Social media algorithms optimize for engagement, and conspiracy content is extremely engaging. It's dramatic, emotionally charged, simplifies complex situations into good versus evil narratives. Platforms don't intend to spread misinformation, but their optimization for user attention inadvertently amplifies content that happens to be false but compelling. The most viral conspiracy theories of 2025 share common elements. They identify clear villains. They explain confusing events with simple narratives. They position believers as informed insiders, while dismissing skeptics as naive or complicit. They're unfalsifiable. Any evidence against them is reinterpreted as proof of the conspiracy's reach and power. These characteristics make them psychologically sticky regardless of truth value. Consider the staged wars theory gaining traction. Recent military confrontations involving Israel, Iran, and the US are claimed to be theatrical distractions, choreographed events aimed at manipulating public attention and oil prices. Supporters point to low casualty numbers, rapid ceasefires, and coordinated media coverage as evidence. Never mind that modern warfare often involves precision strikes that minimize casualties, that diplomacy happens behind scenes before public ceasefires, that media covering wars is normal. The theory persists because it offers a simple explanation for complex geopolitics. The AI controlling governments conspiracy has evolved from fringe to mainstream discussion. The claim is that machine learning systems built for defense, finance, or surveillance have become powerful enough to influence or manipulate leaders without public knowledge. Given that AI does provide recommendations in various domains, and that those recommendations sometimes get followed without deep scrutiny, there's a kernel of plausibility here. But the leap from AI assists decision-making to AI secretly controls everything is enormous. It requires believing that systems reach capability levels far beyond what's publicly demonstrated, that they developed goals independent of their programming, that they coordinate across organizations and governments, that nobody involved has leaked evidence. Each assumption strains credibility, yet the theory spreads because AI development is rapid and poorly understood by most people. The Great Financial Reset theory intensified throughout 2025. Believers claim global elites are engineering total collapse of the financial system to usher in centralized digital economy controlled by entities like BlackRock or the IMF. Elements of this are true. Central banks are exploring digital currencies. Asset managers do wield enormous power. Financial systems are complex and sometimes prone to crisis. But extrapolating from these facts to orchestrated worldwide conspiracy requires ignoring how markets actually work and how difficult coordinating such schemes would be. Weather control conspiracies reignited with unusual climate patterns and massive natural disasters. HAARP, the High Frequency Active Auroral Research Program, gets blamed despite being a scientific facility studying the ionosphere with no capability to control weather. Cloud seeding exists and is used locally, but it influences where precipitation falls, not whether it occurs. Climate satellites observe weather. They don't create it. Yet the theories persist because weather is impactful, unpredictable, and controlled by nobody, which feels wrong to pattern-seeking brains that assume intention behind outcomes. The fake peace deals theory suggests that major diplomatic agreements, especially in the Middle East, are staged and meaningless. Real motives are allegedly resource access, electoral manipulation, or hiding military agendas. This theory is particularly hard to counter because international relations involve deception, secret negotiations, and interests that aren't publicly stated. Some agreements do fail or prove superficial, but claiming all diplomacy is theatre requires vast conspiracies that would be nearly impossible to maintain. UAP disclosure theories occupy strange territory between mainstream and fringe. Government whistleblowers and leaked footage have validated that unknown objects are observed and investigated. Congressional hearings treat the topic seriously, but theories extrapolate from this to claims of alien technology integration, secret treaties with non-human intelligence, preparation for imminent contact. These go far beyond available evidence even as they build on confirmed facts about government programs. The challenge is distinguishing legitimate questions about government transparency from elaborate fiction about alien alliances. UAPs exist as in unidentified objects are observed. Whether they're alien technology, secret human aircraft, natural phenomena, sensor artifacts, or a mix of all four remains genuinely uncertain. Conspiracy theories fill that uncertainty with elaborate narratives that may or may not bear any resemblance to reality. QAnon experienced resurgence in 2025 after fading somewhat from headlines. The theory, claiming a secret cabal of elites is involved in child trafficking and that a coming Great Awakening will bring justice, adapts endlessly to incorporate new events. When predictions fail, the timeline shifts. When evidence contradicts claims, it's reinterpreted as disinformation from the cabal. The theory is essentially unfalsifiable because every outcome gets explained within its framework. Project 2025, despite being a published policy document from think tanks, became conspiracy material through extrapolation. Critics claim it's not just conservative policy roadmap, but a blueprint for authoritarian control, dismantling environmental protections, centralizing power, enforcing religious governance. The document is real and does contain controversial proposals, but theories about military tribunals, civil rights rollbacks, and censorship go beyond what's written, assuming hidden agendas behind stated policies. Interestingly, concerns about Project 2025 mirror conspiracy theories about Agenda 2030, the UN Sustainable Development Goals. Right-wing theorists claim Agenda 2030 is a global socialist plot against freedom, an excuse for lockdowns and control. Left-wing theorists claim Project 2025 is a plutocrat-funded conspiracy to destroy climate action and social programs. Both theories share structure even as they target different political positions. This symmetry is revealing. Conspiracy theories aren't confined to one political orientation. Both left and right generate them, tailored to their respective fears and worldviews. Left conspiracies often involve corporate malfeasance and right-wing plots. Right conspiracies often involve government overreach and left-wing plots. The psychological mechanisms are the same even as the content differs. Fogvid. 24, named for chemical-smelling fog reported across several US states in early 2025, demonstrates how quickly new conspiracy theories form. Scientists attributed the fog to natural weather patterns and industrial emissions. Conspiracy theorists branded it a government bioweapon for population control or mind manipulation. Videos showing drones during the fog events fueled speculation about mass spraying of unknown substances. The pattern repeats endlessly. Unusual event occurs. Mainstream explanation is provided. Alternative explanation emerges that involves malicious intent. The alternative gains traction because it's more interesting and emotionally compelling than mundane truth. Fog from weather and pollution is boring. Bioweapon fog deployed by drones is exciting, terrifying, and creates a clear enemy to oppose. Understanding why people believe conspiracy theories has become serious research focus is not just about misinformation, it's about fundamental human psychology. We're pattern recognition machines. We see connections even where none exist. We prefer simple narratives to complex uncertainty. We trust our social groups and distrust outsiders. We remember confirming evidence while forgetting contradictions. All these cognitive tendencies make us vulnerable to conspiracy thinking. Timothy Tanghelini at UC Berkeley studies conspiracies through the lens of folklore and narrative. He points out that stories are powerful, and we're more comfortable with stories that confirm our beliefs than challenge them. Conspiracy theories are essentially belief narratives, stories we tell that we believe to be true, and they influence our beliefs through repetition and social reinforcement. Once you believe, confirmation bias ensures you find supporting evidence everywhere while dismissing contradictions. Social media removed traditional brakes on conspiracy spread. Previously, sharing bizarre theories required convincing editors, publishers, broadcasters that the content merited distribution. Social media has no such gatekeeping. Anyone can post anything, and if it resonates with audiences, algorithms amplify it. The conspiracy theories that spread fastest aren't necessarily the most plausible, but the most engaging, the most emotionally charged, the most shareable. Research on COVID conspiracies found that theories emphasizing malicious purposes and secretive actions got shared most widely. Theories attempting to provide authentication or sources got shared least. The lesson is clear. Conspiracy theories succeed not through evidence, but through narrative appeal. They tell stories about villains with evil plans, about hidden truths only insiders know, about looming threats that justify action. These elements make compelling stories even when they're completely false. The 5 most popular COVID conspiracies: Bill Gates microchips, 5G network dangers, vaccine side effects, QAnon integration, Agenda 21 depopulation, all shared this structure despite focusing on different specific claims. They overlapped and reinforced each other. If you believed one, you were more likely to believe others because they all fit into an overarching narrative of powerful forces manipulating the population for nefarious ends. This interconnection is crucial. Conspiracy theories don't exist in isolation. They form webs where accepting one makes accepting others easier. Belief in UAP cover-ups connects to beliefs about government secrecy generally. Belief in financial manipulation connects to beliefs about elite control. Belief in technology dangers connects to beliefs about corporate malfeasance. The web of belief grows as new connections form between existing theories. Breaking people free from conspiracy beliefs is extremely difficult. Presenting contradictory evidence often backfires, reinforcing the conspiracy mindset through the explanation that the evidence itself is manufactured by the conspirators. Debunking can increase commitment to false beliefs rather than undermining them. This poses enormous challenges for countering misinformation. Some researchers suggest that rather than attacking beliefs directly, understanding where people are coming from is crucial. Conspiracy theories often emerge from legitimate concerns: distrust of authority, feelings of powerlessness, desire to understand confusing world events. These are reasonable responses to genuine problems. Dismissing believers as stupid or crazy misses the point and entrenches opposition. Building media literacy helps but has limits. Teaching people to verify sources, check multiple outlets, distinguish opinion from reporting, all valuable skills. But when conspiracy theories present themselves with trappings of journalism, citations to studies that don't exist or misrepresent findings, testimony from supposed experts, detecting falsehood requires more than generic media literacy. It requires specific knowledge of the topic and rhetorical tactics being employed. The attention economy incentivizes conspiracy content. Content creators on social media platforms earn money from views, clicks, engagement. Conspiracy theories generate all three. You don't need to believe what you're posting if it pays your bills. This creates a class of professional conspiracy entrepreneurs who may or may not personally believe, but definitely profit from spreading theories. Distinguishing true believers from cynical profiteers is often impossible. Regulation faces severe challenges. Free speech protections in many countries make banning misinformation legally problematic even when socially desirable. Defining what counts as conspiracy theory versus legitimate alternative viewpoint is subjective and politically charged. Platform moderation policies struggle to balance harm reduction against accusations of censorship. There are no easy answers. What's clear is that conspiracy theories will continue proliferating. The conditions that generate them, social media amplification, political polarization, rapid technological change, institutional distrust, aren't disappearing. If anything, they're intensifying. Learning to navigate information environments where truth and fiction mix indistinguishably becomes an essential skill for functioning in modern society. The irony is that some things that sound like conspiracy theories are real. Governments do conduct secret programs, corporations do manipulate markets, technologies do enable unprecedented surveillance. Distinguishing actual conspiracies from false ones requires evidence, not just compelling narratives, but evidence gathering and evaluation are skills most people lack training in. We're left in an uncomfortable position. Conspiracies exist. Conspiracy theories about those conspiracies may be false. Other conspiracy theories may be partially true. Still others may be completely fabricated. Sorting through this requires critical thinking, intellectual humility, willingness to update beliefs based on new information, and tolerance for uncertainty. These qualities are precisely what conspiracy theories discourage by offering certainty and simple answers to complex questions. The future likely involves increasing sophistication of both misinformation and detection. AI tools can generate fake but convincing evidence. Other AI tools can detect deepfakes and fabricated content. It's an arms race with uncertain outcome. Meanwhile, human psychology remains vulnerable to the same biases and heuristics that made us susceptible to conspiracy thinking throughout history. Technology changes. Human nature adapts much more slowly. Comets Lemon and Swan light up October skies. While humanity debates whether spheres carry alien messages and whether quantum computers will break encryption, the universe delivered a reminder that some spectacles need no conspiracy theories or advanced technology to inspire wonder. Two comets, arriving from the frozen depths beyond Neptune's orbit, brightened to naked-eye visibility for observers with dark skies. Lemon and Swan, discovered months apart but reaching peak brightness within days of each other, provided rare opportunities for amateur astronomers and professionals alike. Comet C 2025 A6, discovered by DC Falls using the Mount Lemmon survey in Arizona back in January, is a visitor from the Oort cloud. That spherical shell of icy bodies surrounding our solar system, stretching perhaps a light year from the Sun, contains trillions of potential comets. Most remain frozen and distant. Occasionally gravitational perturbations from passing stars or galactic tides nudge one inward. The comet falls toward the Sun, accelerating as gravity pulls it down the solar system's gravity well. Lemon's trajectory is nearly parabolic, meaning it's probably making its first and only passage through the inner solar system. It spent billions of years at temperatures barely above absolute zero, preserved in pristine condition since the solar system's formation. Now, solar radiation is vaporizing its ices, liberating gas and dust that stream away in glowing tails. The comet is literally evaporating before our telescopes, losing mass that will never be recovered. By late October, Lemon reached 8th magnitude, comparable to the faintest Messier objects visible in small telescopes from dark sites. For context, the human eye under ideal conditions can detect objects down to about 6th magnitude. 8th magnitude is 40 times fainter, requiring optical aid. But photographs with modest equipment could capture it easily, showing the characteristic green glow from carbon emissions and the developing tail. Comet C 2025. R2, discovered by the Solar Wind Anisotropies Space Observatory, SWAN, followed a similar timeline but approached even closer to Earth. At 24 million miles, roughly 1/4 the Earth sun distance, it brightened comparably to Lemon. Having two comets this bright simultaneously is unusual. Most years see none within reach of backyard telescopes. Some years provide one decent comet. Two together offered a celestial treat. The Virtual Telescope project hosted live streams on October the 24th as both comets reached closest approach. Astronomer Giancarlo Massi provided running commentary while telescope feeds displayed real-time images. Thousands watched online as the comets moved perceptibly against background stars, travelling fast enough that their motion became visible over minutes rather than hours. This immediacy connects viewers to the dynamic nature of the solar system in ways that static images cannot. Astrophotographers worldwide captured stunning images. The two comets appeared in single wide field frames, a composition that happens rarely enough to merit special effort. Processing these images requires skill. Comets move relative to stars, so stacking multiple exposures to reduce noise becomes challenging. You can track the stars, making them points but blurring the comet, or track the comet, making it sharp but trailing the stars, or use sophisticated processing to separately stack star and comet data, then combine them. Each approach has merits. Beyond their visual appeal, comets carry scientific importance. They're time capsules from the solar system's formation 4.5 billion years ago. The ices preserve chemical signatures of the pre-solar nebula, the cloud of gas and dust that collapsed to form the sun and planets. By studying cometary composition, we study the raw materials from which everything formed. Spectroscopy reveals what comets contain. Different molecules emit and absorb light at specific wavelengths, creating fingerprints that identify their presence. Water ice is dominant in most comets, but carbon dioxide, methane, ammonia, and complex organic compounds also appear. Some comets show unexpected compositions, perhaps indicating they formed in different regions of the early solar system before getting scattered to the Oort cloud. Lemon's spectrum showed typical comet characteristics. The green colour comes from diatomic carbon, two carbon atoms bonded together, which fluoresces under solar ultraviolet radiation. This molecule is unstable in terrestrial conditions, but persists in the vacuum of space. It breaks down rapidly, so its presence indicates active outgassing. The comet is releasing fresh material, not just displaying a static surface. The dust in cometary tails also deserves attention. These particles range from molecular scale to sand grain size. When Earth's orbit intersects a comet's trail, the particles burn up in our atmosphere, creating meteor showers. The Orionids, peaking around October 21st, derive from Halley's comet debris. Each shooting star is a piece of Halley, typically smaller than a grape but travelling fast enough that atmospheric friction vaporizes it in a flash of light. Studying dust composition reveals the solid materials present in the early solar system. Some grains predate the sun's formation, presolar grains that formed around other stars and were incorporated into the nebula that became our solar system. These grains have isotopic ratios that don't match solar system norms, marking them as foreign. They're literally stardust, material from previous stellar generations now briefly visible as it burns in Earth's atmosphere. The water question matters particularly for understanding Earth's oceans. Our planet's water had to come from somewhere. The early Earth was likely too hot for water to condense. One hypothesis suggests comets delivered significant water after Earth cooled enough to retain it. Billions of cometary impacts during the late heavy bombardment about 4 billion years ago could have supplied the volume of water in modern oceans. Testing this requires comparing Earth's water to cometary water, specifically the ratio of deuterium to hydrogen. Deuterium is heavy hydrogen, a proton plus neutron instead of just a proton. The deuterium to hydrogen ratio in Earth's oceans is well known. Measurements of cometary water from various missions show that some comets match Earth's ratio, while others are significantly different. This suggests a mixed origin for Earth's water. Some came from comets, some came from asteroids, which have different deuterium ratios. Some may have been present in the rocks that accreted to form Earth, released later through volcanic outgassing. Pinning down the proportions requires more measurements from diverse comets and asteroids. Each new comet provides another data point. Lemon and Swan, being fresh visitors from the Oort cloud, carry compositions that reflect where they formed, rather than processing from multiple solar passages. Periodic comets like Halley have orbited through the inner solar system many times. Solar heating has stripped away volatile materials, changing their composition. Long-period comets on their first approach retain original chemistry. This makes Lemon particularly valuable scientifically. Spectroscopic observations during its brightest phase captured data about pristine material from the outer solar system's formation region. That data will be analysed for years, compared to models of solar system formation and evolution, used to refine our understanding of how planets and smaller bodies originated. The comet's nucleus, the actual solid body beneath the glowing coma and tail, is estimated at about 1 mile across, small by solar system standards but containing extraordinary mass. Ice and rock compressed over billions of years into a loosely bound rubble pile that holds together through weak gravity and icy cement. When solar heating begins, the nucleus becomes active. Gas jets erupt from spots where sunlight penetrates surface insulation. These jets push the comet, slightly altering its trajectory through rocket effect. This jet activity makes comet orbits difficult to predict precisely. The gravitational influences can be calculated accurately, but the non-gravitational forces from outgassing create uncertainties. Halley's comet arrives slightly early or late each apparition because of these effects. For newly discovered comets making their first approach, the uncertainty is larger because we don't know their outgassing behaviour. Lemon's trajectory brought it to about half the Earth-Sun distance, 75 million miles at perihelion, its closest approach to the Sun. That's well inside Earth's orbit but outside Venus. The comet is now heading back outward, racing toward the darkness beyond Neptune where it will spend the next few thousand years if it returns at all. The orbital period for parabolic trajectories is undefined. These comets may or may not come back. Swan followed a similar story, discovered by space-based instruments designed to observe the Sun. Swan watches hydrogen emission from the solar wind, but occasionally spots comets as their outgassing creates hydrogen clouds that Swan detects. This discovery method finds comets before ground-based surveys, providing earlier warning and more time to prepare observations. The proximity of Swan's closest approach, 24 million miles, made it particularly attractive for detailed study. Closer means brighter and larger in angular size, easier to resolve structure in the coma and tail. Professional observatories dedicated telescope time to capturing spectra and images during peak brightness. This data will supplement the Lemon observations, providing comparison between two comets from presumably similar regions. Differences in composition despite similar origins would indicate heterogeneity in the early solar system. The Presolar Nebula wasn't uniform. Temperature gradients, turbulence, varying ice condensation distances, all these factors could produce comets with different chemistries, even if they formed in the same general region. Finding patterns in the variations helps map the conditions under which the solar system formed. Amateur contributions shouldn't be underestimated. While professional observatories have larger telescopes and sophisticated instruments, Amateurs provide valuable monitoring. Comets change rapidly. Brightness variations, tail development, outbursts where activity suddenly increases, all happen on timescales of hours to days. Professionals can't watch continuously. Amateurs worldwide provide coverage, reporting changes that professionals then target for detailed study. The community aspect of comet observing creates networks where discoveries and observations get shared rapidly. Someone in Australia spots an outburst. Within hours, observers in Europe and Americas are pointed at the comet capturing data. This distributed monitoring system has been refined over decades and now operates largely through online platforms where observers post images and measurements in real time. Educational value is substantial too. Comets capture public imagination in ways that distant galaxies or asteroids don't. They move, they change, they're temporary visitors that appear, perform, then leave. This creates urgency. If you miss seeing a long-period comet, you won't get another chance in your lifetime. That motivates people to go outside, look up, use telescopes, learn about astronomy. Schools and astronomy clubs organised observing events around the comet appearances, setting up telescopes in dark locations, teaching people how to find and observe the comets, explaining what they're seeing and why it matters. These events often spark lasting interest in astronomy. Someone who sees their first comet might buy a telescope, join a club, become a lifelong observer. The impact extends beyond the specific event. Photographing comets has become more accessible with digital cameras. Film photography required long exposures and careful tracking. Digital sensors are more sensitive, reducing exposure times. Processing software can enhance faint details that might not be visible in individual frames. The barrier to entry has dropped, enabling more people to capture images that would have required professional equipment decades ago. But visual observing retains appeal. There's something immediate and personal about seeing photons that left the comet minutes ago striking your retina directly. No sensor, no screen, just your eye and the light. Experienced observers develop skill at detecting faint objects and subtle details that cameras miss. The human visual system, when adapted to darkness and given time to integrate signal, is remarkably sensitive. Comet tails point away from the sun, pushed by solar wind and radiation pressure. This creates the distinctive shape we recognise, a bright head with streaming tail. But comets actually have two tails, dust and ion. The dust tail is broad and curved, composed of particles that follow Keplerian orbits, but with slight perturbations from solar radiation pressure. The ion tail is narrow and straight, composed of charged molecules swept away by solar wind. These tails can be millions of miles long, despite the nucleus being only miles across. The contrast is dramatic. The Great Comet of 1844 had a tail estimated at over 200 million miles long, reaching beyond Mars's orbit. Modern comets rarely achieve such extremes, but their tails still extend far beyond what intuition suggests possible. The material is incredibly diffuse, essentially vacuum with a trace of atoms and molecules, but it catches sunlight and glows. Observing how tails develop and change as comets approach and recede from the sun provides insights into solar wind behaviour. The ion tail responds to variations in solar activity. When the sun releases a coronal mass ejection, the blast of plasma can disconnect a comet's ion tail, severing it from the nucleus. A new tail then grows over hours to days. These disconnection events are dramatic and provide natural laboratories for studying plasma physics. Both Lemon and Swan will fade now that they've passed closest approach. As they move farther from the sun, solar heating decreases. Outgassing slows, the coma shrinks, the tails dissipate. Within weeks they'll have faded beyond reach of small telescopes. Within months they'll be detectable only by large professional instruments. Eventually they'll be lost in the outer solar system's darkness, unobservable until their next return if that ever occurs. The timing of their appearance, simultaneous with discoveries in quantum computing, debates about UAP disclosure, and conspiracy theories about everything, provides perspective. The universe operates on scales and timescales that dwarf human concerns. Comets orbit for millions of years. They don't care about our politics or technologies or debates. They follow trajectories determined by gravity and physics, utterly indifferent to the dramas playing out on the small blue world they briefly pass. Yet, we care about them. We watch and photograph and study them because they connect us to something larger than daily existence. They remind us that we live in a dynamic cosmos where visitors from the deep arrive periodically, where ices formed billions of years ago can still evaporate in view of our instruments, where the same materials that built Earth and enabled life still drift through space, waiting to tell their stories to anyone willing to listen. The October comet display is over now. The opportunity to observe Lemon and Swan has passed for this apparition. But more comets will come. They always do. Some predicted, appearing on schedule after decades or centuries away. Others surprises, discovered only weeks or months before reaching visibility. Each brings its own characteristics, its own data, its own fleeting moment of glory before returning to darkness. And each reminds us to look up occasionally, to step away from screens and debates and concerns, to find dark skies and see what the universe is offering. Sometimes it's quantum computers achieving impossible speeds, sometimes it's spheres with undecipherable messages, sometimes it's just ancient ice glowing green as it evaporates in sunlight. All of it worth seeing, all of it part of the larger story we're learning to read, the quantum security race. The same quantum computing advances that promise revolutionary drug discovery and materials science carry a darker implication. Everything currently protecting digital information, from banking transactions to state secrets to personal messages, relies on mathematical problems that quantum computers can solve efficiently. The encryption keeping your data private today might be readable tomorrow, and that tomorrow is arriving faster than most security experts anticipated. October brought a demonstration that crystallized the threat. An engineer named Steve Tipperconic successfully cracked a 6-bit elliptic curve cryptographic key using IBM's 133-qubit quantum computer. 6 bits is trivially small by modern standards. Bitcoin and other cryptocurrencies use 256-bit keys. Banking systems use similar or larger keys, but the demonstration validated that quantum attacks on cryptographic systems work in practice, not just theory. The significance isn't the 6-bit key, it's that theoretical algorithms, written decades ago predicting how quantum computers could break encryption, now run on actual hardware and produce correct results. Shor's algorithm, developed in the 1990s, showed that quantum computers could factor large numbers exponentially faster than classical computers. Factoring is the basis for RSA encryption, one of the most widely used cryptographic systems. Current quantum computers don't have enough qubits or low enough error rates to threaten keys of practical size. 256-bit keys would require thousands of high-quality qubits, running complex algorithms for extended periods. We're not there yet, but the trajectory is clear. Each generation of quantum hardware adds more qubits with better coherence. The gap between what quantum computers can break and what currently protects sensitive data is narrowing. Security experts refer to this as the quantum threat timeline. Estimates vary on when quantum computers will be powerful enough to break modern encryption. Optimists say 15 to 20 years. Pessimists say a decade or less. Nobody credible says never. The question is when, not if, and how much warning we'll have before it happens. But there's a more immediate problem called harvest now, decrypt later. Adversaries can copy encrypted data today and store it. When quantum computers become capable, they decrypt the stored data retroactively. Anything that needs to remain secret beyond the quantum threat timeline is already at risk. Medical records, financial data, state secrets, intellectual property, communication logs, all potentially vulnerable to future decryption. This creates urgency around quantum-resistant cryptography, also called post-quantum cryptography. These are encryption methods based on mathematical problems that even quantum computers struggle to solve efficiently. Lattice-based cryptography, hash-based signatures, multivariate polynomial systems, code-based encryption, several approaches show promise. The question is which ones are truly secure and practical to deploy. The National Institute of Standards and Technology, NIST, has been running a standardization process for post-quantum cryptography since 2016. Multiple rounds of evaluation winnowed dozens of candidate algorithms down to a handful approved for use. These standards represent years of analysis by the cryptographic community, testing the algorithms against all known attacks, including quantum ones. But standardization is only the first step. Implementation takes years. Every system using vulnerable encryption needs updating. Protocols need changing, software needs rewriting, hardware in some cases needs replacing. The Internet's infrastructure, built over decades, deeply embeds current cryptographic methods. Swapping them out is like replacing the foundation of a building while people live in it. Australia made headlines by deploying a quantum-secure link between Quintessence Labs, CSIRO, and ARNet. This system uses quantum key distribution QKD, which leverages quantum mechanics itself to create provably secure encryption keys. The principle is elegant. Quantum states change when observed. Any attempt to intercept the key distribution gets detected because the interception disturbs the quantum states in measurable ways. QKD has limitations. It requires specialized hardware, fiber optic links between parties, and works over limited distances before signal loss becomes problematic. You can't quantum key distribute over the open internet, but for critical links, government-to-government communication, financial system backbone, data center connections, QKD provides security that no future computer, quantum or otherwise, can break because it's based on physics rather than math. The Australian implementation shows quantum security transitioning from laboratory to operational deployment. It's not a demonstration or test, it's protecting real data on production networks. If someone attempts to tap the line, the quantum signals change and alarms trigger. The system provides an early warning that conventional encryption lacks. Britain installed its first quantum computer in Manhattan, an interesting reversal of technology flow. Oxford Quantum Circuits deployed their Genesis system at a data center, integrating with NVIDIA AI superchips for hybrid quantum AI workloads. The system serves finance and security sectors, indicating that quantum computing is transitioning from research to commercial application in sensitive domains. The concern isn't just protecting data at rest or in transit, it's also protecting the algorithms and models that AI systems use. As AI becomes more capable and economically valuable, the intellectual property in trained models represents enormous investment. If quantum computers can reverse engineer or steal these models, companies lose competitive advantage. New forms of protection will be needed. Quantum Motion, a UK startup, announced the first full-stack quantum computer fabricated using standard silicon CMOS technology. This matters because it means quantum computers can be manufactured using the same facilities that produce regular computer chips. Current quantum computers require exotic materials and specialized production. Being able to use existing semiconductor fabs dramatically reduces cost and increases scalability. The system fits in 3 standard server racks, including the dilution refrigerator that cools it to operating temperature. That's remarkably compact. Early quantum computers filled rooms. Getting them down to rack scale enables deployment in existing data centers without massive infrastructure changes. It also makes them more accessible to organizations that can't build dedicated quantum facilities. But capability and accessibility make the threat more acute. If quantum computers become commonplace, available through cloud services or installed in corporate data centers, the timeline for breaking encryption compresses. Currently, only a handful of organizations worldwide have quantum computers approaching useful scale. In 5 years, hundreds or thousands of organizations might have access. Some will be adversaries. The cryptographic community is racing to stay ahead, migrating to post-quantum algorithms before quantum computers become powerful enough to threaten current encryption. But migration is slow and expensive. Small companies and developing nations may lack resources to upgrade. This creates vulnerability asymmetries where some organizations and countries are protected while others remain exposed. There's also the unknown unknowns problem. Post-quantum algorithms are based on problems believed to be hard even for quantum computers. But our understanding of quantum algorithms is incomplete. Maybe someone discovers a quantum algorithm that efficiently solves lattice problems, or breaks one of the other candidate systems. Then we're back to square one, needing new approaches. Classical cryptography had decades to mature. Algorithms were proposed, attacked, refined, attacked again. The ones that survived extensive analysis became standards. Post-quantum cryptography is compressing this process into years instead of decades. We're confident the selected algorithms are strong, but confidence isn't certainty. Cryptographic surprises have happened before. The RSA algorithm itself is example. When proposed in the 70s, it seemed secure against all known attacks. Over time, improved factoring methods reduced the key sizes considered safe. 256-bit RSA keys, once adequate, are now breakable with sufficient computing power. Key sizes increased to stay ahead of improving classical algorithms, but quantum algorithms represent discontinuous jump rather than incremental improvement. They break the assumptions underlying multiple current systems simultaneously. Elliptic curve cryptography, widely used because it provides security with smaller keys than RSA, is also vulnerable to quantum attacks. Digital signatures, authentication systems, key exchange protocols, many cryptographic building blocks need quantum-resistant alternatives. The migration is complex because these pieces interoperate. You can't just swap one component without considering how it interacts with others. Blockchain systems face particular challenges. Cryptocurrencies like Bitcoin use elliptic curve signatures to authenticate transactions. If quantum computers can forge signatures, they can steal coins by impersonating owners. Some cryptocurrencies are exploring quantum-resistant signature schemes, but implementation is complicated by the need for consensus across decentralized networks. The social coordination required for cryptographic migration is substantial. Everyone needs to upgrade roughly simultaneously. If some users adopt post-quantum algorithms while others don't, they can't communicate securely. Standards help but don't guarantee coordination. Legacy systems that can't be upgraded remain vulnerable indefinitely. Hardware security modules, HSMs, are specialized devices that store cryptographic keys and perform encryption operations in tamper-resistant environments. Banks and governments use them to protect sensitive operations. Many deployed HSMs don't support post-quantum algorithms. Replacing them is expensive and logistically complex. But if they remain vulnerable to quantum attacks, they become liabilities rather than security enhancements. Military and intelligence implications are particularly concerning. Encrypted communications between commanders and forces, between allied nations, between agents and handlers, all depend on cryptographic security. If adversaries develop quantum computing capability before we transition to post-quantum systems, they gain intelligence advantage. Historical communications become readable. Current operations become compromised. This has driven substantial government investment in quantum computing and quantum security research. The strategic implications are comparable to nuclear weapons or space programs. Whichever nations lead in quantum technology gain advantages in multiple domains simultaneously. Computing power for AI and simulation, cryptographic security for communications, code-breaking capability against adversaries, sensor technology for detection and navigation. The public-private partnership model is being applied, with government funding university research while companies commercialize results. This accelerates development compared to purely government or purely commercial efforts. But it also creates security challenges because research results get published and companies operate in global markets. Controlling technology spread becomes difficult. China has made quantum technology a strategic priority with massive investment. They've demonstrated quantum satellite communication and claim progress on various quantum computing approaches. Whether their systems match or exceed Western capabilities is unclear because information is controlled, but assuming they're behind is dangerous. The quantum race has genuine competitors. The quantum key distribution network China built demonstrates ambition. Ground stations connect via quantum encrypted links. Satellites extend the network beyond fiber optic range. The system creates communication infrastructure that's quantum secure today, not waiting for post-quantum algorithms to be developed and deployed. Whether it works as advertised is debated, but the effort is real. Europe's quantum initiatives focus on both computing and communication security. The Quantum Internet Alliance is developing continent-spanning quantum networks. Individual countries have national programs. The goal is ensuring European digital sovereignty, the ability to protect data and communications without depending on foreign technology. This geopolitical aspect adds urgency beyond purely technical considerations. The encryption debate about balancing security with law enforcement access becomes more complex in the quantum era. Some governments want backdoors and encryption to access criminal communications, but backdoors that let law enforcement in also let quantum computer-wielding adversaries in. The concept of lawful access assumes you can create selective vulnerability. Quantum attacks make selective vulnerability untenable because any weakness becomes catastrophic. This might force policy changes. Either we have strong encryption that even quantum computers can't break, meaning law enforcement loses access except through other means like endpoint compromise, or we have weak encryption that anyone with sufficient quantum computing capability can break, meaning privacy and security become impossible. The middle ground of controlled weakness collapses under quantum attack threat. Financial systems are beginning to take notice. Banks are exploring post-quantum cryptography for transaction security. Credit card processors are evaluating algorithms. Stock exchanges are planning migrations. The financial sector learned from Y2K that major technology transitions require years of planning and execution. Starting early reduces crisis risk. But there's no hard deadline like Y2K provided. We don't know exactly when quantum computers will threaten current encryption. Could be a decade, could be sooner if there's a breakthrough, could be later if progress stalls. This uncertainty makes planning difficult because investing heavily now might be premature while waiting might be too late. The arms race aspect is unsettling. Once someone has quantum computing capability that breaks encryption, they gain enormous advantage. Incentives exist to develop the technology secretly, deploy it covertly, exploit the advantage before others catch up. This creates a period where one actor has capability while others don't, with all the strategic implications that entails. Verification becomes crucial. How do we know if an adversary has developed quantum code-breaking capability? They won't announce it, they'll exploit it quietly. Evidence might emerge from intelligence failures or compromised systems, but attribution is difficult. Was it quantum attack or conventional breach? The ambiguity itself is destabilizing. Treaties or agreements limiting quantum computing development face enforceability problems. Quantum computers don't emit radiation or require rare materials that can be monitored. They're built in the same facilities that produce conventional computers using similar supply chains. Detecting undeclared programs would require intrusive inspections that nations would resist. So regulation happens through export controls and technology sharing restrictions, which slow but don't prevent proliferation. The transition to quantum-resistant cryptography is humanity's largest coordinated security upgrade, larger than any previous cryptographic migration because it affects every digital system simultaneously. The timeline is uncertain but not infinite. At some point, quantum computers will break current encryption. Whether we're protected when that happens depends on how quickly we migrate and how soon the threat materializes. It's a race with moving finish lines and uncertain positions. But one thing is certain, it's a race we can't afford to lose. What's coming next? The 48-hour forecast. Stand back for a moment and look at what we've covered. A metallic sphere with undecipherable symbols that might be alien technology or elaborate art. Quantum computers achieving 13,000 times speed up over the world's fastest supercomputers. Nobel Prizes recognizing that quantum mechanics works at scales we can engineer. Congressional hearings treating UFO disclosure like a serious policy matter with roadmaps to 2034 contact. Discoveries inside our own planet revealing its violent birth. AI deployments at scales where 500,000 employees at major corporations use it daily. Conspiracy theories spreading faster than facts. Comets from the edge of the solar system providing views our ancestors would have called omens. And a race to protect encryption before quantum computers break everything. Each of these could fill hours of discussion alone. Together they paint a picture of civilization at an inflection point where multiple trajectories converge. Technology accelerating, public awareness shifting, questions that seemed settled being reopened, mysteries accumulating faster than solutions. The 48 hours of October 2025 delivered more significant developments than some entire years. But what connects them? Is there a pattern? Or are we just experiencing random fluctuations in the information environment, seeing connections that don't exist because our brains are wired to find patterns even in noise? Maybe both. Some connections are real. Quantum computing enables AI advances which create new security threats requiring quantum solutions. That's a genuine loop. Other connections might be illusory, seeing conspiracies linking unrelated events into elaborate narratives that feel true but aren't. The Boogosphere exemplifies this uncertainty. If it's alien technology, it connects to UAP disclosure as evidence that we're not alone. The symbols might be a message we need quantum computing and AI to decode. The timing of its appearance amid other revelations could be significant or coincidental. We don't have enough information to decide definitively, so people choose what to believe based on prior inclinations, availability of evidence, emotional resonance, social influences. This is where we are as a species, caught between expanding knowledge and expanding mystery, every answer revealing new questions, every solved problem exposing deep complexity. The universe keeps surprising us, and whether those surprises come from aliens or quantum mechanics or our own technologies almost doesn't matter. They're transformative either way. The quantum computing revolution is perhaps most concrete because it's measurable. Google's demonstration didn't rely on testimony or ambiguous data. They ran an algorithm, compared results to classical computation. The quantum computer won by overwhelming margin. This is fact, reproducible, verifiable. What it means for society, how quickly it develops, who controls it, those remain uncertain, but the core capability is established. Within 5 years, we'll likely see quantum computers tackling problems with immediate practical value. Drug candidates screened for effectiveness before expensive trials, materials designed computationally then synthesized for testing, chemical reactions simulated to optimize industrial processes. These applications don't require magic. They require quantum computers with enough qubits and low enough error rates to run useful algorithms, and we're approaching that threshold. The Nobel Prize recognition accelerates this timeline. It validates the field, attracts talent, justifies investment. Students seeing quantum computing honoured at the highest level choose it for careers. Governments seeing strategic importance increase funding. Companies seeing commercial potential launch products. Awards like Nobel don't just recognise past achievement, they shape future direction. The UAP disclosure trajectory is harder to predict because it depends on factors we can't observe. If there's genuine evidence of non-human technology, someone somewhere knows. Whether they'll reveal it, under what circumstances, on what timeline, those decisions get made in classified settings we have no access to. Colonel Nell's roadmap to 2034 might be accurate, informed by knowledge we lack, or it might be optimistic speculation dressed as planning. But disclosure momentum is real regardless of what gets disclosed. Congressional hearings continue, legislation advances, whistleblower protections get debated. The infrastructure for revelation is being built whether or not there's anything to reveal. This changes the landscape. If disclosure occurs, the mechanisms exist to manage it. If nothing extraordinary gets revealed, we've at least forced transparency about what the government does and doesn't know. The conspiracy theory problem won't resolve easily. The conditions creating them, social media amplification, institutional distrust, information overload, political polarization, aren't going away. If anything, they intensify. AI-generated content will make distinguishing truth from fabrication even harder. Deepfakes improve constantly. Text generation is indistinguishable from human writing in many contexts. Images and videos can be synthesized convincingly. This creates what some call epistemic crisis. How do we know what's true when technology enables perfect forgeries? When experts disagree and we lack expertise to judge? When sources we trusted prove unreliable? The traditional verification methods, trusting institutions, checking credentials, comparing sources, all become less effective as both real and fake content become more sophisticated. One response is developing AI tools to detect AI-generated content. Watermarking, forensic analysis, provenance tracking. These help, but face arms race dynamics. Detection improves, generation adapts to evade detection. Detection improves again. There's no permanent solution because the technologies co-evolve. We're likely stuck in permanent uncertainty where some content is verifiable, some is obviously fake, and much falls in ambiguous middle ground. Another response is shifting from content verification to source verification. Don't ask if this video is real. Ask who produced it and what their track record is. This relies on reputation systems which have their own problems, but might be more robust than trying to analyze each piece of content independently. Trusted sources remain trusted until they demonstrate untrustworthiness. Verification happens at the producer level rather than product level. But both approaches require media literacy, critical thinking, intellectual humility, skills that aren't universally distributed and are difficult to teach. Someone determined to believe will find supporting evidence regardless of its validity. Someone open-minded might still be deceived by convincing forgeries. Perfect solutions don't exist. We muddle through, doing our best with imperfect information and limited cognitive resources. The space discoveries point toward a near future where we answer fundamental questions about life beyond Earth. Europa Clipper launched recently and will study Jupiter's moon for signs of habitability. Dragonfly will eventually reach Titan to explore its exotic chemistry. Mars Sample Return, if funded, will bring rocks to Earth for definitive analysis. Within a decade, we might know if life exists or existed elsewhere in our solar system. That knowledge would be transformative even if the life is microbial. It would prove life isn't unique to Earth. It would suggest that wherever conditions allow, life emerges. Given billions of stars with trillions of planets, life would be common rather than rare. The universe would be teeming with biology even if intelligence is scarce. That changes how we see ourselves, our planet, our responsibilities. Finding evidence of past life on Mars would be particularly profound. Mars was wet and potentially habitable billions of years ago. If life arose there independently from Earth, it would indicate life emerges readily. If Martian life is related to Earth life, sharing common ancestry, it suggests life transferred between planets via meteorite impacts. Either conclusion is scientifically revolutionary. The AI trajectory points towards systems that are genuinely useful assistants rather than party tricks. The enterprise deployments happening now test whether AI can enhance productivity at scale. If they succeed, adoption accelerates across industries. If they fail, there will be recalibration and more careful implementation. But the technology isn't going away. It's too useful for specific tasks, even if general intelligence remains distant. Concerns about AI safety grow louder as capabilities increase. Bengio warning about extinction risk within a decade isn't dismissed as easily as similar warnings from less credible sources. The people who built AI are increasingly worried about what they've built. That should give everyone pause. They understand the technology better than anyone and they're concerned. Whether those concerns are warranted remains debated. Some AI researchers think existential risk is overblown, distracting from present harms. Others think it's the crucial issue that overshadows everything else. The disagreement is genuine and both sides make reasonable arguments. What's clear is that we're creating powerful tools without fully understanding their implications. That's not unusual. Most technological revolutions happen that way, but it's uncomfortable when the tools might be smarter than their creators. The quantum security race has clear timelines, even if exact dates are uncertain. At some point, quantum computers will break current encryption. Before that happens, we need to migrate to quantum-resistant algorithms. The window for safe migration is closing but hasn't closed yet. How this plays out over the next decade will determine whether we experience smooth transition or crisis. Financial systems, governments, militaries all have incentives to migrate early. The cost of transition is high, but the cost of being vulnerable is catastrophic. Expect accelerating deployment of post-quantum cryptography over the next few years. Standards exist. Implementations are being tested. Large-scale rollouts will begin soon if they haven't already in classified settings. Individual users will benefit from these migrations without necessarily knowing they're happening. When your bank upgrades encryption, your account becomes quantum-resistant. When messaging apps adopt new algorithms, your conversations gain protection. Most security improvements are invisible to end users. They just work in the background, protecting data and communications from evolving threats. The comet visits remind us that while human concerns dominate daily attention, the universe continues regardless. Rocks and ice orbit according to physics, indifferent to our hopes and fears. These visitors from the deep will return to darkness and cold, preserving their ancient chemistry for millennia, until perhaps disturbed again by gravitational nudges that send them sunward. There's something humbling about that perspective. We're not the centre of anything except our own narratives. The cosmos is vast, old, and operates on scales that make human lifespans look like eye blinks. Our civilizations rise and fall while comets orbit. Our technologies advance, but stars still fuse hydrogen regardless. This isn't nihilistic. It's perspective that helps calibrate importance. What matters in the immediate term? The decisions we make about technology development and deployment. Whether we manage to maintain cryptographic security through quantum transition. whether AI systems remain beneficial as they grow more capable, whether disclosure of UAP information, if it comes, is managed transparently or creates chaos, whether we can distinguish truth from fabrication in increasingly polluted information environments. These are human problems requiring human solutions. They don't have predetermined outcomes. The future isn't fixed. It's shaped by choices individually and collectively. Whether quantum computing benefits humanity or harms it depends on how we develop and govern the technology. Whether AI helps or hurts depends on similar choices. Whether we handle potential alien contact wisely or poorly is up to us. The convergence of developments in October 2025 might be coincidence. Technology advances on multiple fronts simultaneously because they are all driven by similar forces: scientific progress, engineering refinement, commercial incentives, geopolitical competition. Or maybe there are connections we're only beginning to perceive. Quantum computing enabling AI breakthroughs which reveal patterns in data, including UAP observations which require new physics to explain. Either way, we're living through interesting times. That old curse, "may you live in interesting times," applies. Interesting times are uncertain times. Times when established patterns break and new ones emerge. Times when small choices have large consequences because systems are in flux. Times when the future feels both thrilling and terrifying because anything seems possible. The 48-hour forecast is more of the same but accelerated. More quantum advances, more AI deployments, more disclosure momentum or more obfuscation depending on what there is to disclose. More conspiracy theories because conditions creating them intensify. More space discoveries as missions return data and new telescopes begin operations. More everything because the pace itself is increasing. Information velocity keeps rising. What took years to discover now takes months. What took months takes weeks. The lag between discovery and public awareness shrinks. We live closer to the cutting edge of knowledge than any previous generation. That's exhilarating and overwhelming. Keeping up requires constant attention. Falling behind happens easily. But maybe keeping up isn't necessary. Maybe trying to track every development is misguided. Perhaps better to focus on what matters personally while maintaining awareness of broader trends. The universe will reveal its secrets at its own pace. Our understanding will grow whether we stress about it or not. The technologies will develop according to physics and economics regardless of how closely we watch. This doesn't mean passivity. It means choosing battles, focusing attention where it's most effective, accepting that we can't know everything or understand everything or control everything. Do what's possible, advocate for what's important, learn what's interesting, but don't pretend omniscience or omnipotence. We're finite beings in an infinite universe, doing our best with limited time and knowledge. The mystery of the boogosphere will eventually resolve one way or another. Either it's proven alien technology which revolutionizes everything, or it's proven human creation which teaches lessons about belief and verification, or it remains ambiguous, joining the long list of anomalies that neither confirm nor deny extraordinary claims. Whichever outcome, we'll learn something. The quantum computers will continue improving, error rates will drop, qubit counts will rise, algorithms will be refined, applications will multiply. In 10 years, quantum computing might be mundane. A specialized tool used for specific problems like GPUs are used for graphics or machine learning. Or it might be revolutionary, transforming industries and enabling breakthroughs we can't imagine yet. Most likely, somewhere in between. The AI systems will grow more capable. They'll handle more tasks, integrate more deeply into infrastructure, become more reliable, or reveal more flaws. The debates about safety and ethics will continue, probably intensifying as capabilities increase. Regulations will emerge, inadequate at first but evolving. We'll muddle toward frameworks that balance innovation with protection. The UAP disclosure will proceed or stall depending on factors mostly hidden from public view. Congressional pressure might force revelations, whistleblowers might release information that can't be ignored, or the topic might fade again as it has before, dismissed as distraction from more pressing concerns. We'll see. The timeline is uncertain, but the attention isn't going away soon. The space missions will return data. Some will confirm expectations, some will surprise us. Our understanding of the solar system and galaxy will deepen. We'll find more exoplanets and characterize their atmospheres. We'll learn more about our cosmic origins and evolution. The knowledge accumulates whether or not it includes aliens. The conspiracy theories will mutate and spread because human psychology hasn't changed, even as information technology has. We'll keep seeing patterns, inferring intentions, seeking simple narratives for complex realities. Some theories will prove partly true, most will be false. The challenge of distinguishing them will remain, and life will continue. People will work and love and raise children and create art and solve problems and make mistakes. The grand developments we've discussed matter, but they matter in context of ordinary human existence. Technology serves humanity, not the reverse. Whether quantum computers crack encryption or AI writes novels or aliens visit, the fundamental human experiences persist. We seek meaning, we form communities, we want to understand our world, we create stories to make sense of experience, we hope for better futures and fear worse ones. We're curious about mysteries and uncomfortable with uncertainty. These drives shaped human culture for millennia and will continue shaping it regardless of technological change. So what's coming next? More of everything, more knowledge and more questions, more capability and more risk, more connection and more isolation, more clarity and more confusion. The pace accelerates, but human nature adapts slowly. We'll handle what comes as we've always handled new developments, imperfectly but persistently. Some will thrive in the changes, some will struggle. Most will adapt well enough to continue. The universe doesn't care about our theories or our technologies. It simply is, vast and ancient and full of wonders. We're privileged to study it, to gradually decode its secrets, to understand how it works and our place within it. That quest continues regardless of political dramas or conspiracy theories or even alien contact. The pursuit of knowledge is fundamentally human. As long as we exist, we'll keep asking questions and seeking answers. October 2025 was remarkable for the convergence of developments across multiple domains. But every month brings discoveries. Every year advances understanding. The specific events we've covered will be footnotes to future historians studying this period. What they'll recognize is that we lived through acceleration, when knowledge and technology both expanded rapidly enough to be disorienting. Future generations might look back enviously at this time of discovery and possibility, or they might view it as a narrow escape from disaster as we navigated dangers barely understood. Either way, we're living the history they'll study. The choices we make, individually and collectively, matter because they shape what comes after. That's true in every era, but feels more acute now because the pace and stakes both seem higher. The 48-hour forecast? More breakthroughs, more mysteries, more debates. The patterns we've examined will continue and intensify. Quantum computing will progress, AI will spread, UAP disclosure will advance or stall, conspiracies will proliferate, space missions will deliver data, and somewhere, someone will discover something that shifts everything again, starting a new cycle of wonder and investigation and argument. That's the nature of science and technology and human curiosity. There's no endpoint where we know everything and build nothing new. Every answer is provisional, every achievement a platform for the next challenge. The journey continues as long as we do, and based on everything covered here, the journey is just getting interesting.